Good afternoon, my dear NEET warriors. This is your Captain Shreyas, and I'm going live on the one and only #1 NEET English channel of all the students preparing for NEET 24, 25, 26, and that's your Vedantu NEET English. And we are on the block 1. Block 1 carries a weightage of 120 marks. And yesterday, Diksha ma'am had an amazing class of inorganic chemistry. If you have not checked that out, do check it out. Monday and Tuesday, Gopika ma'am and Basa sir are going to finish the block 1 of biology as well. And within 4 blocks, we'll be completing the entire syllabus, all the high weightage topics, and we will ensure that your scores are boosted by as much as possible. And today in block 1, we are doing modern physics, which includes atoms, nucleus, photons, duality, semiconductors, and logic gates. So I'm seeing the Josh in the chat box. Very good, my dear students. I hope I'm audible as well as visible. Yes, I'm audible and visible. Let me just check. Yes, it is. Good afternoon. Hello Pratibha, hello Sanju, Krishna, Chandan, hello Munia, hello Revati, hello Jan Lisa, hello Rathanveri Gara. Wow. Namaskaram. Hello Pratibha. Good afternoon. I hope I'm visible also properly. Yeah. Let me just check once so that I also feel satisfied. Yeah. Yes, I am able to see myself. Very good. Cool. Chalo, let's begin with the class. And this is your Captain Shreyas, who has been sending kids to all the top-notch government medical colleges and AIIMS. I've been teaching for more than 13 years now. And here I am, yet again, one more year to produce these amazing results. And this time, it's your turn. You have to make not just me proud, but your parents proud. You yourself should feel proud the moment, you hear the result, and the moment you talk about your college and the way in which you are pursuing your MBBS degree, right? So let's begin, and smash the like button and also subscribe. Yeah, very important. Subscribe. I need to keep telling you, or else you will miss this channel, you'll miss the videos, you will be like, oh my god, where was this? I don't want all that to happen, right? So make sure you subscribe. So let's begin with the first point, which is photons and duality. Then we'll go to photoelectric effect. Then we'll go to atoms, then nucleus, then semiconductors, and then logic gates. It's going to be a long class, expect 4 to 5 hours, right? And also we'll have a small break in the evening, okay? So when we talk about photons and duality, let's understand that light has a multiple personality disorder. Just like in the school you are very well behaved, in the house you act like a fool, like a maniac, or maybe the other way around. In front of your friends you are very cool bro, but at the home you are like very silent. Same way, light also has multiple personality disorder, and it has two kinds of behavior. One is a wave behavior, and the second is basically the particle behavior. This wave behavior you study in the chapter of electromagnetic waves. Light is an electromagnetic wave given by Maxwell, basically Maxwell's theory, right? You would have studied that. But the particle nature is studied under this particular chapter. It is given by Einstein and Planck theory, where we are going to see the concept of light as a particle. Now the particle of light is called as a photon. Just like the wave is an electric magnetic fields wave, the particle of light is a photon. So there are experiments which show light behaves like a wave. There are experiments which show light behaves like a particle. So that's why we say it has what? Dual nature, dual faced. So it has dual nature. That is why it is called dual nature of light. And Pandu is also back in the chat box. Nice to see Pandu after a very long time. Great. Now, just like light can have dual nature, D Broglie thought, can normal matter around us, for example, Pandu, Champa, me, you, this board, the chair, the table, the computer, the camera, everything, does that also have dual nature? So when we talk about matter, when we talk about basically matter, we have generally seen the particle behavior. We have seen the particle behavior, and the particle behavior is nothing but its mass. Its mass. The matter, I am made of mass, you are made of mass. Yes, the chair, the table, the wall, the ceiling, everything is made of mass, the matter, atoms, electrons, protons, neutrons. So is it also going to have wave-like behavior? Is it also going to have wave-like behavior? Yes, that is called as matter wave. That is called as a matter wave. Now you might be thinking, is that electromagnetic in nature? The answer is no, it is not electromagnetic. It is a new kind of wave. Like the ocean wave is different than sound wave, is different than the wave on a string, is different than the ripples of water, is different than electromagnetic wave. Same way, this is a new kind of wave which is called matter wave. You cannot see it with your naked eye, you will not feel it, but it is there. Experiments have been conducted to prove that these waves exist, right? They are called as matter waves. Now this theory was given by whom, guys? This was given by basically none other than D Broglie. D Broglie. D Broglie. This mass phenomena is contributed to mainly Newton and so many people. Newtonian mechanics, what we have studied in mechanics, kinetic energy, momentum is mass into velocity, force is mass into acceleration. So mainly attributed to Newton. Is this basic flow chart clear of how light has duality? Even the normal matter, electrons, protons, neutrons, Pandu's mass, Champa's mass. Pandu also has dual behavior sometimes. Pandu sometimes, says, I love you, Champa. Pandu sometimes says, who are you, Champa? So dual behavior. So this is again dual nature. This is also again dual nature. Very good. Now that you understand this, let's study what are the different properties. What are the different properties of photon? And then see, we have studied wave nature, that is a separate chapter. In this chapter, we are going to basically focus on this part. We are basically going to focus on this part, and we are also going to focus mainly on this part. So these are the two things which we are going to focus on, because this you have already studied in another chapter, electromagnetic waves. This you have studied in Newtonian mechanics. Is this absolutely clear? Everybody give me a thumbs up. Did you understand what is exactly what we are going to study in this particular chapter? Yep. Perfect, perfect. Let me know by giving up a thumbs up in the chat box. Very nice. Keep it going, guys. Keep it going. Now, what are the different properties of a photon? So let's talk about photon. What is photon? First of all, it is the particle. It is the particle of light. It is the particle of light. Now, what are the different properties of a photon? Number one property, the packet of energy of light, the packet of energy of light is basically called as a photon, meaning light's energy does not go continuous. It is not continuous, it goes in packets. It goes in packets. Imagine, I'm not going to do this. I drink this water. Okay, I drink lots of water, put it in my mouth. I don't swallow it. And then I start spitting it like a fountain, like a nice fountain. Continuously it is coming. That is continuous. Like packets means I spit at one place, spit at another place, spit at some other place. So that is packets. So light's energy goes in packets. That packet of energy which we call as the quanta. Quanta. Understood, guys? Very stupid example I gave, but I hope you visualized Shreyas sir, creating a fountain with his mouth and, giving packets also. Yeah, very good. Now, that quanta of energy, the packet quanta means the same thing. Quanta means a part of it. It's a packet kind of a thing. So the quanta of energy which every photon has is given by E photon. E photon is nothing but hf, where f is the frequency, h is called as the Planck's constant, which you can also write it as hc divided by lambda. Reason is the wave associated with it, is given by c is equal to f times of lambda. F is frequency, lambda is the wavelength, c is the speed of light, which is 3 into 10 to the power 8 meters per second. Is that right? 3 into 10 to the power 8 meters per second. So frequency is c divided by lambda. That is the energy of the photon, where I can also write h, which is nothing but your Planck's constant. Planck's constant is nothing but 6.6 10 to the power minus 34 in SI units. Okay, the normal units that you use, that is what it is. Is that okay? Everybody with me? Cool till this point? Perfect? Okay. Now, usually when you substitute these values, h value, c value, lambda value, it becomes usually difficult to calculate. To make our calculations easy, we have a number which we can remember very easily. So, instead of writing hc by lambda, we can also write it as approximately 1240 divided by lambda. If this lambda is in nanometers, this answer will be in electron volt. You can also write it as 12400 divided by lambda. If this lambda is in Armstrong, the final answer will be in electron volt. So you can usually use these numbers to specially solve the problems in a much simpler manner. I will give you an example to demonstrate this. Say for example, they tell you the wavelength of light. The wavelength of light is 200 nanometers. What is the energy of the photon? That is the question. So the energy of the photon, because it is measured in nanometers, I will use this formula. Lambda in nanometers 1240. So what will I write? 1240 divided by lambda, which is basically 200 nanometers. This 0 will cancel. Remember, the final answer will be in electron volts. 124 divided by 2 is nothing but 62. So it will be nothing but 6.2 electron volt. So that is the energy of the photon. Everybody understood? Understood? Clear? So one extra 0 you will add for Armstrong. That extra 0 is not there for nanometer. 2 zeros for Armstrong, 1 0 for nano. 1 0 for nano, 2 zeros for Armstrong. You can think Armstrong has the dot, no? Armstrong has the dot, right? So one extra dot like 0, anda. One egg is there. One extra egg is there for Armstrong. Nano does not have that. Okay? I hope till this point everything is clear. Absolutely. So moving ahead to the next pointer. That is all photons, what do? They travel at the speed of light. They travel at the speed of light, which is 3 into 10 to the power 8 meters per second. These photons, they possess momentum. And the momentum of these photons is given by Planck's constant by lambda. Planck's constant by lambda. We can also do a small modification over here. I can multiply by c, divide by c, and I will put lambda over here. What is hc by lambda? What is hc by lambda? It is nothing but energy. So it is energy of the photon divided by c. That is the momentum. So either this formula or this formula, one and the same thing. Either this formula or this formula, one and the same thing, guys. All these are important formulas. This was energy momentum relationship. Here we found the energy of the photon in terms of the wavelength. Of course, speed of light is frequency into the wavelength. These are all standard formulas. Okay, this was a special value which you had to remember. Cool till this point? Shall we go ahead? Okay. Now one thing which you cannot write for a photon, this is wrong. Momentum is not equal to mass into velocity. Reason is mass of a photon is not even defined. Mass of a photon is not even defined, so never ever write momentum is mass into velocity. It is h by lambda. Okay, mass of a photon, it's meaningless. There is no, sense to it. There is no sense to it. But we also call that the rest mass, we also say the rest mass is 0. You'll be wondering, sir, what is this rest mass and general mass? In Einstein's complex theory of relativity, when mass begins to move, the mass changes. So we do not have all that. Just understand, when the mass is at rest, it is 0. When it is in motion, there is no sense to it to talk about what is the mass. So this is one pointer as a theory point, remember it. Otherwise, no understanding part is required. Also remember, you cannot write kinetic energy as half mass into v square. This is wrong. You cannot even write it as p square by 2m. This is also wrong. Okay, kinetic energy is half mv square or p square by 2m because mass only is not defined. So do not include any equations which have mass in the formula. Is that right? Everybody, keep all these things in mind. Very good. Moving ahead to talk more about photons. Whenever these photons are more in number, the light's intensity is more. And when they are less in number, the intensity of light is less. So the intensity of light depends on the number of photons which are falling. But remember, intensity of light is also defined as like this. It's the energy, the total energy rather. I will put it over here. It is the total energy of the photons per unit time, per unit area on which they are falling. So the intensity symbol that we use is generally I. The total energy which we talk about the photons will be something like this. N number of photons are there. Each photon has an energy E photon, but per unit time, so I have to divide it by T and the whole thing divided by area. So basically this will become N by T into energy of each photon divided by A. That becomes the intensity of the light. That basically becomes your intensity of the light. If you ask me what is the unit of intensity, it is very simple. Energy per time is nothing but joules per second divided by area, meaning per meter square. So joules per second is watts. So it is watt per meter square. That is the unit of intensity. Thank you, Krishna, for all the lovely blue hearts. Yeah. Yes. Dulasi, today's session will also cover atoms and photoelectric effect. We are starting off with photons. Without understanding photons, how will you understand atomic spectra and how will you understand photoelectric effect? That's the reason why we start with photons first. Is that right? Everybody? Cool. Perfecto. So these were some of the important properties of a photon. Okay, what we have studied. I hope you have made running notes, and if you are like, so why did you tell me now? I did not make any notes. Don't worry. In the description box, there is a Telegram group. Join that group and I'll be sharing all these notes for your benefit. Okay, don't worry about it. In the PDF form, don't worry. We are going to send all the notes. Okay, now let's go to the next part. Remember, what did I tell you at the beginning only? If I go back to the first slide over here, we'll be discussing the particle nature of light, which is basically called photon. Next thing which we'll be discussing is the wave nature of the matter. Wave nature of the matter, which was given by D Broglie. So this part, properties of photon, basic properties we have seen. Let's go to the wave nature of it. Let's go to the wave nature of it. Okay. Wave nature of the particles. Okay. Now, matter waves. Next thing is matter waves. Matter waves. This is nothing but the wave nature of mass. Wave nature of mass. Now, D Broglie was a very smart guy, and if you see what he did, you will be also astonished. Wow, sir, he's brilliant, crazy fellow. What he said was, okay, listen, we have light, okay, and light has two kinds of behavior, okay, and one is wave, one is particle. Wave nature has wavelength, frequency, etc. Cool. The particle nature has momentum, right, and energy and all of that. So the momentum of light is given by h by lambda. So what he saw was, look at this, when I say momentum of light is h by lambda, this lambda was representing the wave nature of the light, and this was momentum, which was the particles momentum. In this case, the particle was none other than photon. So he applied brilliant mind. He used his brilliant mind, and what he did was he moved lambda on the top and he put momentum below. He put lambda on the top and he put momentum below. And this is true story. I am not kidding. You might be thinking Shreyas sir is chumma saying this, but no, this is how D Broglie actually did this. And what he did was, now, okay, so if this momentum is now the masses momentum, then what should this represent? What should that represent? Come on, think about it. If just like over here, you know, this wavelength was the wavelength of light. This was nothing but the wavelength of the matter wave. Not of light, wavelength of the matter. Wavelength of the matter wave. This is exactly what D Broglie did. And people praised him a lot. I wish I was in that era. Numerator into denominator, denominator into numerator. Thousands of people would have clapped for me. Wow, brilliant, sir. Amazing. So he did this, people clapped for him. This is also called as your D Broglie wavelength. This is also called as your D Broglie wavelength. D Broglie wavelength. Very, very important formula. If you know this, you know this. It's the same thing. If you know this, you obviously know this, right? Very good. So now, what is the meaning of this? What is the meaning of this? When I say lambda is equal to h by p, meaning if there is a mass, it is going with some velocity. It definitely has some momentum. Anything which has momentum has a matter wave behavior also. It has a wave-like behavior also, which is called the matter wave. And that wavelength, and that particular wavelength is lambda, which is given by h by p. This is your matter wave. I have seen so many teachers explaining this, saying that, oh, you know what matter wave is? This mass which is there, no? It goes like this. I was like, what nonsense. It does not do all these things. Okay. So when you find the wavelength of any mass, it is not the actual manner in which it is going. No, no, no. There is another thing associated with it which you cannot feel, you cannot see, you cannot sense it. You have to conduct special experiments for that. Only then you will be able to associate that. So guys, please understand that this wavelength is not the actual manner in which the your matter goes. Okay, this is what basically this relationship stands for. This relationship stands for. Now over here, is it okay or not okay for me to say momentum is mass into velocity? Can I say this or no? Because if you remember correctly, then you will remember that in case of light, mass into velocity is not the momentum. But do you think over here it is justified? Yes or no? Put it up in the chat box. Obviously it can. Obviously it can be, because that's how you have learned momentum in the Newtonian mechanics. So there is nothing wrong in writing momentum is mass into velocity. In fact, I can also say kinetic energy is half mv square. No issues, no problem at all. And also I can write it as momentum square by 2m. No issues, no problems. From this, do you see, if 2m is taken over here, 2m is taken over here, what will it become? What will it become, my dear students? Momentum square will become 2mk, 2m into k. So momentum will become root of 2mk. So this is also often used in many situations. This is your extended formula. This is your extended formula, right? H by root of 2mk. K is nothing but your kinetic energy. This is your kinetic energy. Kinetic energy. Got it, my dear warriors? Everybody till this point clear? Awesome. Now that you understand, okay, momentum, wavelength, kinetic energy, momentum, kinetic energy, wavelength, this is what the relationship is. When to use this and when not to use this is also clear. Here you couldn't use half mv square because mass is not defined. The moment mass is not defined, anything which has mass, do not use it for light. But for actual particles, protons, electrons, alpha particles, neutrons, Pandu, Champa, me, blackboard, fan, tube light, everything you can use it. Okay, you can use it. All right. Now there are special problems like this where a particle is accelerated by delta V volts. Then you will have to find the D Broglie wavelength. D Broglie wavelength. How do you do these kind of questions? If a particle of some charge and some mass is basically accelerated to get some particular velocity, let's say v, the moment it gets velocity, it definitely has momentum, and therefore it also has its own de Broglie wavelength. It also has its own de Broglie wavelength. This de Broglie wavelength will be h by p, which means it will be h by root 2 mk and all of that. But the problem is I do not know the kinetic energy because I do not know the speed. No issues. What we can say is, because it has been accelerated, can I say the electrical energy which it received because of the acceleration by this voltage will convert into kinetic energy? So the energy of electrostatics, the electrical energy which it gets, converts it into the kinetic energy of the particle. Kinetic energy of the particle. What is the increase, or what is the electrical energy given to it? It is always nothing but the charge. It is the charge multiplied by the potential difference. This is equal to your kinetic energy. What is the charge? It is Q. What is the voltage difference? Delta V is equal to K. Now coming back over here, till this point everybody clear? Everybody clear? Very good. So this will become h by momentum is root 2 instead of k. Okay, no worries, I'll write it over here. Instead of k, what do I put? 2m into q into delta V. That's it. That will become your final expression for the de Broglie wavelength in terms of the accelerated voltage. And then comes even more special formula. Lambda is equal to this h by root of 2mq delta V for an electron. This formula is very, very special. The mass of the electron, I think, is close to 9 into 10 to the power minus 31. The charge of the electron is 1.6 10 to the power minus 19. H is nothing but 6.6 10 to the power minus 34. You substitute everything. What do you get is lambda is equal to 1.227 divided by root of delta V, but this is in nanometers. It's in nanometers, mind it. So what is this formula helping me with? Simplifying the calculations. This is just like this part over here. Hc by lambda, it helped me in simplifying the result. The one which I did over here, right? The calculation of energy became very simple. By substituting wavelength, I get the energy. I don't have to substitute h, c and all those nonsense. Here also, I don't have to substitute mass, charge, put it under root, h, convert into everything. No, my job is going to be simplified. So that is why you will obviously remember this particular result. Is that right, everyone? Very good.
I didn't catch that. Could you try again?
Okay, very good. Awesome. Let's move on to the next question now. Let's move on to the next concept actually. Okay, so till this point, I hope everything is clear. We have done kinetic energy, we have done charge, mass, everything. Okay, great. Yeah, so this part is done. I think we can directly start with some questions then. Okay, fair enough. The photon of frequency nu, see in physics, I generally don't use nu. Why? Because it is confusing with speed or voltage. So in chemistry, you will see mu symbol. In physics, you will see most of the physics teachers will use F. Okay, unless they are just bahating from the books, they will use like mu. But you know, most of the clever physics teachers will use the symbol F. Okay, has a momentum associated with it. The c is the velocity of the light. The momentum is how much? Come on, my dear students. What do you think is the correct answer for this? Put it up in the chat box. I want everybody spamming the answer. The momentum of the light photon is the momentum of the light photon. This is the question. Momentum of the photon. What's the formula for momentum? It is h by lambda. But I want the answer in terms of frequency. C is equal to f lambda. Bring lambda below. F will be there on the top only. C will go over here. So instead of 1 by lambda, you can put it as f by c. But over here, the symbol for frequency is nu. So h nu by c. Option D. D for Diksha ma'am. D for doctor. Okay. D for AIMS Delhi also. Wow, so many things you got. D for Diksha ma'am, D for doctor, D for Delhi AIMS. Very good, Karika, Anuradha, Sanju, Krishna, Pratibha, Swatantra. Awesome, Mahi. Very good, Dark Frozen. Proud of all of you guys. See, you are understanding the concept and you are able to apply it. You should feel very, very happy about yourself and you are happy and you know it. Don't clap your hands, just smash the like button. Okay, just smash the like button. The relationship between the energy of the photon and its wavelength is directly proportional, inversely proportional, independent, none of the above. What do you think is the right answer for this? Between energy of a photon and the wavelength, we just studied energy of a photon is hc by lambda, which is also hf. Don't you see? It is inversely proportional. Energy of the photon is basically inversely proportional, guys. Yes, option B is correct. B for Busvasaurus, sir. B for Busvasaurus, sir. Yes, very good. Yeah, B for biology, B for botany, B for Busvasaurus, sir. Very good. Awesome, awesome, awesome. Cool. Let's move ahead to the next question. Coming up on your screen. If an alpha particle and proton are accelerated by the same potential difference, the ratio of their de Broglie wavelength will be, come on my dear students, alpha particle and proton by same voltage difference, the ratio of the de Broglie wavelength. So lambda, remember, is h by p and momentum was root 2 mk if you remember, and when you accelerate it, the kinetic energy becomes charge into voltage difference. Remember guys? Yeah. So voltage difference is same, h is same, 2 is same, therefore lambda is inversely proportional to root mass, also root of charge. So now let's come back. So wavelength of de Broglie of alpha by proton will be, since it is inversely proportional to root of mass, so mass of alpha below, mass of proton on the top. Here inversely proportional to root of charge, so charge of the proton on the top, charge of the alpha particle below. Mass of the proton, if it is m, alpha will be 4m. Charge of the proton, if it is e, of the alpha will be basically 2e, correct? 1 by 4's root is 1 by 2. This is nothing but root 2. So it will be 1 by 2 root 2. 1 by 2 root 2. Be careful. Alpha is there and proton is there. Many students are writing 2:1. What just happened, guys? What just happened? Be little bit careful. Be little bit careful, since why would it be 2:1? Yeah, be little bit careful. Be little bit careful. Right? Alpha by proton. So mass of alpha will be below. Charge of alpha will also be below. Charge of alpha will be 2e. Proton will be e. Mass of proton, if it is m, alpha is 4m. So root of 4 is 2 and root of 2 is root 2. So 2 root 2 is there below. So 1 by 2 root 2. Be little careful. Okay. See if some silly mistake was done. Maybe you forgot this charge ratio. Most of the students might have just taken this mass, forgot the charge. If that was a mistake, realize it and don't repeat it in the final exam. Happens. These kind of mistakes do happen at times. Okay. No worries, but don't repeat it. This was a NEET 2020 question. If you can solve it, very happy. An electron is accelerated from rest through a voltage of this. De Broglie wavelength of the electron is this. The potential difference. Guys, this number looks very familiar to me. This number looks very familiar to me. Do you remember where we saw this number? Where we saw this number? We just saw it, right? Somewhere. Remember? And that too for an electron. Oh yeah, sir. It was 1.227 nanometers by root of the voltage difference. Yes, sir. We saw it, sir. Wow, very good. So over here the wavelength is 1.227 into 10 to the power minus 2 nanometers is equal to 1.227 nanometers by root of delta V. So 1.227 nanometers, 1.227 nanometers. Tata bye bye. Tata bye bye. So 10 to the power minus 2, if I square it, I will get 1 by delta V. So delta V I will get basically 1 by 10 to the power minus 4, which is 10 to the power 4 volts. 10 to the power 4, D for doctor, D for Delhi Ames, D for Diksha ma'am. Very good. Perfect. That is the correct answer. See, you guys got it? Yeah, so easy it was. NEET 2020 question, Corona question. This is also called as the Corona question. NEET was delayed. Students kept on preparing. My goodness, 2021 also. D for dirty Pandu. Ooh. Webu? No. Please don't call Pandu dirty. And people, D for dedicated Pandu looks, sounds nice. Yeah, D for dedicated Pandu is good. Yeah, cool. So moving on to photoelectric effect. Photoelectric effect. Now that you understand what photons, what the energy, what the wavelength and all these things are, I think it's a good time we go on to the photoelectric effect. Now, before going to photoelectric effect, I have a simple question for all of you. This is very, very interesting. This is very, very interesting. If I tell you the number of photons per unit time are same. This is the number of photons per unit time are same for two different colors. One is blue color and one is your red color. The question is, compare the intensities. Compare the intensities of light. Compare the intensities of the light. Come on, my dear students. What do you guys say about this? What do you guys say about this? Intensity formula. What was the intensity formula? If you remember, it was N by T into energy of the photon by your area. So intensity is dependent on this, which is same. Area, let's say it is same. So it is directly proportional to the energy of the photon. That means intensity, because it is directly proportional to the energy of the photon, which is also hc by lambda. So it is inversely proportional to the wavelength. It is also inversely proportional to the wavelength, yes or no? Now out of red and blue, out of wavelength of red and wavelength of blue, can you guys quickly tell me who has more wavelength? Who has more wavelength, guys? Obviously red's wavelength is more, blue's wavelength is less. So intensity of blue will be more or less. When wavelength is less, intensity is more. So less wavelength, intensity is more. So this would be the correct relationship. So the intensity of blue light will be more than the intensity of the red light. Is that clear? So intensity, if you see it properly, it is also dependent on the color. But for the same color, it is directly proportional to N by T. More photons go, more intense the light will be. More photons will go, more intense the light would be. As simple as that, right? That is how it works. Very good. Clear? Yes? Awesome. Let's now talk about photoelectric effect, because you will see it does have that concept of intensity of light also, where number of photons per unit time is talked about. Now imagine there is a house. In that there is a Pandu, and then Pandu's parents are also there here, like this. Okay, and this is Pandu's friend over here. This Pandu's friend wants to call Pandu for some nice meeting, get together, movie, some chill out place they want to hang out. Okay, so this guy comes into the house, rings the doorbell, parents open the door. They're like, is Pandu there? Yes, Pandu is there, but he is studying. Please auntie, there is some function and this and that, we want to party. You will get one tight slap. They'll be like, don't disturb again, get lost. Has it ever happened to you? I think it would have happened. So then you improvise on this. You think, okay, I need more convincing power to get Pandu out of the house. So again, next day you go, auntie, is Pandu there? Yes, Pandu is there. Okay, auntie, actually we are planning a get together for group studies. We are going to prepare for NEET. Oh wow, you are going to prepare for NEET. Okay. And we have got the topper's notes. Amazing. Pandu, go. Your friend has come. You can go for studying. Pandu goes out of the house and these two people chill out. Happens, right? Okay. Now the same thing also happens with light. Just imagine there is a metal surface. The metal surface is like parents. The metal surface is like your parents. Oh. The electrons is like Pandu. Electrons is like Pandu. Pandu's friend is basically like light. The light which falls is Pandu's friend. Pandu's friend. Okay. Light falls, Pandu's friend comes, enters the house, metal. It falls on that metal. Parents. It has to convince, means it has to have good energy. If it does not have good energy, this Pandu, basically this electron, will not be chucked out of this metal. It will not be able to come out. If it is puss, it is like no convincing power, means very little energy, this electron will not come out. If it has good energy, this electron will come out. This Pandu will come out. Understood? This is basically called as photoelectric effect. This is basically called as photoelectric effect. Very easy, no? This is exactly photoelectric effect, guys. The whole chapter, Einstein made an equation on this. So this Pandu will basically be ejected out. If what? If the light has good energy, good amount of energy. The energy over here is symbolic to the convincing power of Pandu's friend. It's a symbolic representation of Pandu's friend's convincing power. Kem cho majama? It's your only Lisa. Oh my God, I never knew I have only my Lisa also. Next level fan following, guys. Thank you so much. Okay. So let's have a look at the photoelectric effect. So you have a metallic surface. And then you have multiple colors or multiple wavelengths of light, starting off with the red wavelength, which is falling onto it. Then maybe you change the wavelength to, let's say, for example, green. And then you slowly make it to violet. Violet has very small wavelength. Remember that. Okay. Now, out of these three wavelengths, can you guys quickly think and tell me which light has the most energy? Guys? Captoelectric effect. Oh my God, thank you. Which light has the most energy? The one which has the smallest wavelength. Who is that? This guy. More energy. So the chances of the electron coming out are highest where? Here, right? So the electrons might be ejected over here very easily because of the high energy. Maybe red, which has the least energy, might not have enough energy to chuck it out. So maybe no photoelectric effect might be there. No photoelectric emission happens. These electrons which are ejected out, they are also called as photoelectrons, right? Here maybe the electrons come out but with very little juice, means they just come out, just ejected. Oh, which means this wavelength is a critical wavelength and this frequency is also critical frequency. This is also called as the threshold wavelength and frequency, where the photoelectric effect just happens. Just enough. The Pandu's friend is like begging to the parents, please, auntie, please send Pandu. It's okay, I'll just come back in 1 hour. Please, just for some time. Like, okay, you take him only for 1 hour, not more than that. I want him back. So that is what is happening over here. Awesome. So here no photoelectric effect, here photoelectric effect just happened. So in that case, whatever energy is there of the light, the energy of the light photon is just enough to take it out. So that is called as the work function. Is that clear? That is called as a work function. The minimum energy needed, it is basically the minimum energy needed to check it out. Needed to check it out. So energy of the photon is nothing but hf naught, or you can also write it as hc by lambda naught, and that is equal to the work function. That is the formula which we got. Here in this particular case, obviously this frequency is more than the threshold, than the threshold frequency. It is more than the threshold frequency. Here the frequency is less than the threshold frequency. Here the frequency of the red is less than the threshold frequency, so it is not able to give any photoelectric emission. Wavelength wise, if you see, the wavelength will be more. The wavelength will be more than the threshold wavelength. Here you will see the wavelength is less. The wavelength is less than the threshold wavelength. Okay, I hope this is absolutely very clear. Yes, Pandu, work function. That is how I have seen people say it. Are you Gujarati? I have a lot of Gujarati friends, yeah. Lot of amazing people I have. And I learn a lot of things from Gujarati people. Yeah. Every person has many things to, teach you. Yeah. Crazy. The way they do business and the way they manage so many things. It's something really you should be proud of. And I have some friends who are really hardworking, especially these Gujaratis who, are having these shops or having some businesses. Get up in the morning, they go to the business, they work day and night, and they come back and, they don't feel tired or they don't complain. And like, okay, next day I have to do this. Crazy, next level stuff. So now that we have understood it till here, these photoelectrons which come out, from this metallic plate, from this particular metallic plate, if I collect it on the other side, and I don't let it go anywhere out, that means I need to keep it in a vacuum tube, I need to keep it in a vacuum tube so that the electrons don't go out anywhere. And then I collect these electrons and I bring it back over here. This is crazy, right? Imagine this. This is crazy. I bring it back over here. So now I have a small current which is set up in the circuit. So there is a graph which one can draw very easily. And that is, how will your current versus the wavelength graph look like? Tamil Nadu students, they have other things to teach us. And I'll tell you, most of the authors and most of the learned persons I've seen, most of the Indian authors I've seen, and especially, these economists and all are from Tamil Nadu. Mathematical brains usually come from Tamil Nadu. That is what is the speciality I have seen. Yes. So maximum wavelength that you can have is lambda naught. If the wavelength exceeds lambda naught, no photoelectric effect occurs. That is the reason why this graph will be basically like this. Basically, it will cut out over here. Okay, this is basically your lambda naught. Before this, there is photoelectric effect. After this, there is no photoelectric effect. Understood? As simple as that. Moving ahead now to the next concept. Imagine this is your metallic surface. And I do two comparisons. First time, the light which is falling, let's say the light which is falling is having little bit less intensity. Then the light which is falling has more intensity. That means more rays of light are falling on it. This is more intense light. If the light is more intense, What can you say, my dear students? More photons will be falling. So here, if there are these many number of electrons which are ejected out, because the light is more intense, more photons will collide, they will take out more electrons. So you will see more electrons, more photoelectrons coming out of it, more photoelectrons coming out of it. Is that right? So if you connect a circuit like this, right, you will see the current will also increase proportional to the intensity. So on the x-axis, if I put intensity, and this is nothing but your current, this is nothing but your current, and this is nothing but your intensity of the light, you will see that the graph which is there, it is going to be a straight line. It is going to be a straight line. So the current is directly proportional to the intensity. More light, more photons, more photoelectrons, more electrons, more conduction, more current. All of them are directly related to each other. Is that right? Everybody clear till this point, my dear students? Awesome, awesome. Clear? Shall we go ahead to the next part? Very good. Now that these electrons are coming out, imagine this. This was the light falling on the metallic surface. These electrons which are ejected out will have different energy. Not all of them will have the same energy. Do you understand why they are not of the same energy? Just think about it. The same friend goes to multiple people's house. Okay? Some pandus will come out very easily. Some pandus will be very difficult to bring them out of the house. Right? So you can think that their resistances could be different. And when these electrons come out, some electrons are already there on the surface, so easily they come out. Some electrons are deep inside the surface. So when the light photon falls onto it, by the time they find their way and come out, they will be already tired and they will have little bit less energy. So you will see that the photoelectrons have many, or they have different kinetic energies varying from 0 to some maximum kinetic energy. 0 to some maximum kinetic energy. Beyond that, you will not have any electron having more energy than the maximum. You will be like, sir, why, sir? Think about it. The luckiest electron who does not lose energy. The photon comes, you need some energy to pluck it out, you give it, and whatever is remaining is there with the electron. It does not collide anywhere, it does not hit anything, that's it. All that energy is for the electron. It has maximum amount of energy, right? It has maximum amount of energy, right? Wow. So Einstein thought, how about making an energy equation? So here it goes. The energy of the photon had 100 laddus of energy. In that 100 laddus of energy, some energy was spent to remove that electron. Basically, let's say 20 laddus had to be fed to take out that electron, which we call as the work function. Right? What will be the remaining? Be as? It will be there as the kinetic energy. Maybe what happens is the electron collided with something. So maybe there was a loss. Out of the 100 laddus, maybe 10 laddus were lost. So how much kinetic energy will be remaining? 20 and 10 becomes 30. So to make it 100, I will have to put 70 laddus over here. So the kinetic energy of that electron which lost 10 laddus will be just 70. But imagine the luckiest electron. Imagine the luckiest electron. This is what Einstein thought. The luckiest electron, the work function will still be 20. There will be no loss. So the kinetic energy of such a guy, will be nothing but 80. Oh my God. This is basically the maximum kinetic energy. This is basically the maximum kinetic energy. Got it? Everybody? So then he made the famous photoelectric equation. He said the energy of the photon is equal to work function, which is phi, plus the maximum kinetic energy. He made this, and for that he won Nobel Prize. For this he won Nobel Prize and explaining, obviously he wrote a paper properly explaining everything. This equation, Einstein got Nobel Prize. Can you believe that? Crazy, no? One simple energy equation. This is next level stuff. Next level stuff, guys. So work function plus maximum kinetic energy is the energy of the photon. Let's play around with this. We are going to play around with this now. Phi, I already know. It is nothing but, we just saw over here, phi is nothing but hf naught or hc by lambda naught. Energy of the photon, we know this, hc by lambda. Okay. What is Kmax? How do I measure Kmax? No issues. Let's measure Kmax. How to measure Kmax? Here is what I do. Okay. This is my photoelectric surface. On that, some light is falling. And what I do is I collect these electrons which are ejected at different speeds. They are all having different speeds. Some have less speed, some have more speed. And I collect it on the other side. But this time I apply a voltage. That is the interesting part. Because these are negative charges. And I want to measure the kinetic energy, I will try to stop them. Hey, stop. I want to stop them. I want to deaccelerate them. That means the force should be downwards. How do I ensure force is downwards? Think about it. How do I ensure that the force on them is downwards? The field, how will the electric field be? Think about it. This is negative charge. So the field should be in this direction, in this particular direction. Only then it will work. So the field should be in this direction, electric field. So to keep the electric field in this direction, because it's a negative charge, remember, force and field will be opposite in direction. That means this should be at a higher voltage. This should be at a lower voltage. That means you connect it to the positive terminal of the battery like this. You connect it to the positive terminal of the battery. But this battery is a variable voltage. All right. Variable voltage means you can change the voltage as per your requirements. So if I increase the voltage difference increases, field increases, force increases. It will be difficult for the electron to reach here. Maybe few electrons reach who are having very high energy, very enthusiastic electrons. But beyond a point, even the luckiest electron won't be able to reach on the other side. Getting my point? Even the luckiest electron will find it to reach on the other point because you have increased the voltage so much. So the potential which is basically reversed, the reverse potential which you are applying to stop it, the reverse potential to stop the current, that is called as the stopping potential. What is it called? Stopping potential. Stopping potential, which is having a symbol of Vs. Exactly. Reverse potential, negative, because you are reversing. Yeah. So can I then say that whatever kinetic energy maximum was present of that electron has completely gone against the electrical potential energy, guys. And what is electrical potential energy? I just gave it to you. It is charge multiplied by potential difference. What is the charge? Electron charge. What is the voltage? Vs. This is nothing but K max. This is nothing but the maximum kinetic energy. Is that clear? That is how you measure it. What a brilliant way to understand. So now, can I rewrite this equation? Maybe. Why not? So, if I have the energy of the photon is equal to the work function plus the K max, this is called as photoelectric equation. Photoelectric equation by Einstein's photoelectric equation. The energy of the photon, I can use either hf naught, or I can also, sorry, not f naught, I can use hf or just hc by lambda, it's completely up to you, is equal to work function. Again, I can use hf naught, or I can also use hc by lambda naught. Remember, this is the actual wavelength of light used. This is the threshold wavelength or threshold frequency for which photoelectric effect just begins. Completely different things. And kinetic energy max, that is nothing but E times of Vs. It is E times of Vs. Sometimes you also write it as half mass of the electron into the speed maximum square, Vmax square. All these things are the same thing. Is this clear? How do we write Einstein's photoelectric equation? Einstein's photoelectric equation in various forms. It's completely up to you how you want to write it. Now, if you play with this equation a little bit, observe how. I will write it as hf is equal to hf naught plus E times of Vs. Let's play with it a little bit. EVs is nothing but hf minus hf naught. I have shifted this guy over here. That's why it becomes minus. I divide by E. So Vs will become h by E into f minus h by E times of f naught. Now, if you want, I can further write this as Vs is equal to h by E into f minus hf naught is work function by E. Why am I writing it like that? Observe carefully. If I compare Vs with y, if I compare f with x, if I compare h by E with m, this is equal to, this is plus, and c. Y is mx plus c. What is it? Y is equal to mx plus c. It's an equation of a straight line. So, let me draw the y-axis and the x-axis. X-axis will have frequency. Y-axis will have stopping potential. It should be a straight line. It should be a straight line with a slope of h by E, and h by E is always going to be a constant, and it should also have y-intercept. Y-intercept is basically negative. Y-intercept is negative, which is nothing but phi by E. The y-intercept C is nothing but minus phi by E. So hence I should get it as a straight line with a negative intercept. So it should be like this. It should be basically like this. This point will be minus phi by E. Minus phi by E. This guy's slope will be h by E. H by E. Is that right? That is a very, very important graph. If I use a different metal altogether, then it will be just parallel to this. It will just hit this y-axis at a different point. That's all. Phi will be different because phi is dependent on the material. Understand this. So this y-intercept depends on the material. Depends on the metal. Depends on the metallic surface. The slope is a constant. It is not dependent only on anything. It is not dependent only on anything. Got my point, my dear warriors? This is a very crucial graph. All the graphs that I have been giving you, no matter where, here, right, or even before this, all these things, they are all very, very important. There is one more graph though. There is one more graph though, which you should understand. And for that, my question to you is, will this stopping potential depend on intensity of the light? What do you guys say? If I make the light more intense, more photons will fall. Will the voltage required to stop them be more or less? Think about it. See, just by increasing the light's intensity, yes, more photons will fall. Yes, more electrons will come out, but the energy of the electrons won't increase. Because just increasing the light's intensity means there are more number of photons, but of the same energy. HF, 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 HF. Now there are more HFs, but each photon still has HF energy only. So the electrons which come out also have the same energy, same kinetic energy they have. So to stop them also I will need the same voltage. That is why I will not see any change in the stopping voltage if I increase the intensity of the light. And that's what I want you to understand over here. So I'll mention that changing intensity of light has no effect on stopping potential, but only changes the current. That is number one. Number two, this point is clear. Number two, second point. Imagine more and more light falls. You keep on increasing the intensity. Okay. And let's say instead of reversing the voltage, you apply a forward voltage. Meaning you accelerate the electrons. The moment you accelerate the electrons, even the slow moving electrons will reach on the other side. So what will you see? An increase in the current. You will see an increase in the current. But if you increase the voltage, forward voltage, not reverse, forward voltage more and more, do you think it will be of any benefit beyond a point? Because whatever light is falling, it's doing its job, it's ejecting the electrons. As many electrons had to go out, they went out. Increasing the voltage more will not create new electrons. That's it. So you will still see the number of electrons reaching the other side will be the same. Will be basically the same. So after a point, there is no use. It's like, imagine there are 10 kids in a classroom and a friend of them goes to the classroom. Hey, come, let's go out. Maybe 2 friends come. Next day he goes, hey, come, let's go out. Maybe 4 friends come out. Next day he goes and says, hey, come, let's go out. All the 10 people come out of the classroom. Next day if he goes and says, I am more energetic, I am more enthusiastic, let's get 20 people out of the classroom. My goodness, there are only 10 kids in the classroom. How will you get 20 people out of the classroom? Getting my point? So as many electrons had to be ejected, they came out. So increasing any voltage will not create new electrons which will create more current. So it will get saturated. So that is the reason why I'll put the next pointer over here. When forward voltage is increased, the current increases till saturation, and beyond that no further change happens. All of this statement can be put into a graph like this. Oops, 1 second. Can be put into a graph like this. This is your current and this is your voltage. On this side, it will be considered as forward voltage. There is no voltage here. This side will be the reverse voltage. So the graph looks something like this. You can see it has become saturated. It has become saturated after a certain voltage. The current does not increase beyond that. Here the current becomes 0. So this is your stopping voltage. This is your stopping voltage. Do you understand why the graph looks like this? Do you understand why the graph looks like this? Everybody with me on this? Yep, very good, very good, very good. Excellent, excellent. Next, if I increase the intensity of the light, what will happen? The current will increase, but the stopping potential has no effect, right? Because of the intensity of the light. So that is why you will see the graph go up like this for more intense light. For more intense light, the graph just goes up like this, but the stopping voltage is still going to be the same. No effect on the stopping voltage. This is also a very, very important graph. Oh, thank you so much. Looks like we have somebody in the chat box. Maybe either Disha ma'am or Gopika ma'am or Basvasaurus sir. One of them. Thank you, Zai, Pandu, Krishna, Jen Lisa. Thank you, Tommy. Thank you so much, Vabu, Dark Frozen. Means a lot. Thank you. It's your only Lisa. Thank you, Nischala. Thank you, Abhisha, for keeping the Josh high. Are you now ready to solve some problems? But just before we start with the problems, let me tell you, there are 3 ways of getting the Pandu out of the house. Meaning the 3 ways to get electron out of the metallic surface. So electron emission can happen via one of these 3 ways. What are the 3 ways? The first one we just saw, that is your photoelectric effect. This happens because of light falling onto it. The second one is basically called as thermionic emission. Meaning this happens because of heating, temperature and heat. You heat the metallic surface. When you heat it, what happens is these molecules begin to dance. More temperature, they will dance even more. Okay, here and there. And when they dance, they will hit each other, they will collide each other, and you will see these electrons will be knocked out of their orbits and shells, and these electrons will be let go. So you will see electron emission happening over there also. Okay, great. And then what about, okay, I am very scared. I just did the dance. Now I am scared that Pandu is also in the chats. I might become a meme. I might see a reel on Instagram very soon. Oops. Okay, anyways, now it has happened. I can't undo it. So last one is called as field emission. Field emission. Field means electric field. So a strong electric field or basically a strong potential difference like lightning. What happens? The charge from the cloud, zzz, it comes out, right? Because of a strong voltage difference, sparks between 2 wires, strong field which is there, strong voltage which is there, creates spark. That is also electrons being emitted. Got it? Everyone? Clearo? Understood? Awesome. Pandu is like, Capto has given me the content. Oh my god, this is next level. I'm waiting now, Pandu, for what is your creativity going to look like on Instagram. Alright, cool. So these are the 3 different ways. You should just know about it, nothing more. Mainly this thing people don't understand. So what is this field emission? Lightning, man, sparks, man. That is all. Strong voltage creating that electrical discharge between a non-conductor. Actually, air was not a conductor, but it became conducting because of a strong electric field which pulled that electron out from here to there. That's all. Okay, let's start with some questions coming up on your screen, and here it is, the first one. What does it say? Light of 2 different frequencies whose photons have energies 1 electron volt, 2.5 electron volt successfully illuminate a metal of work function 0.5 the ratio of the maximum speeds of the emitted electrons will be. Okay, read the question again and again. Sometimes when you read it once, twice, maybe things will be clear. Where is JEE paper discussion, Mukesh? Not on the NEET channel, on the JEE channel. I think it is going on. I just finished 15 questions. Guys, it is going to be a crazy day for me today. I just did my JEE paper discussion. Now maths and chemistry must be going on. I'm back here. And after this, I'll again go back and discuss the JEE paper on the JEE channel. Okay? So that is how things are with Captain Shreyas sir. How much hard are you guys working? Chandan, better go through NCERT also for some hidden lines here and there. But 99% of the syllabus will be done through the notes. Okay? 99% of the syllabus. Some things here and there, just go for it. Okay? Yeah. Cool. So what do we do over here? See, energy of the photon is work function plus kinetic energy, which is half mv square. Okay. So for the first person, for the first light of 1 electron volt, yeah, the energy of the photon is 1. The work function is basically 0.5 plus half m v1 square. So half m v1 square is nothing but 1 minus 0.5, which is basically 0.5. Now do the same thing for the next person. So the next light has a energy of 2.5. Work function is 0.5 plus half m v2 square. So therefore half m v2 square will be 2.5 minus 0.5, which is 2. Alrighty. So let's basically divide both of them. So divide this and see what do you basically get if you divide both of this. So I'll get v1 by v2 whole square is equal to 0.5 by 2. 0.5 by 2, which is 1 by 4. Therefore, v1 by v2 will be 1 by 2. So 1 by 2 is C for Captain Shreyas. There you go. That's it. That is the answer. Awesome. Clear? Clear? Mukesh, physics will be there after some time because we switched the streams, right? So once the video ends, YouTube will take some time to stitch it, and maybe after half an hour or 1 hour, you will be able to see the complete video. Okay? Don't worry. Because I was not in the studio in Bangalore. I mean, I'm in Bangalore, but not in the studio. That's the problem. Okay. Cool. Let's move on to the next one on your screen. The voltage of the cell is fixed. The photocell means light falls onto it. The current flows from one metal to the other metal. So there is a voltage created. So that is a photocell. Photo means light, cell means voltage. Okay, so photocell. Basically, photoelectric effect is happening and you have kept the voltage same. That means whatever battery that you are connecting across the plates is the same. The light which is falling onto it is changed. Lambda is changed. How will the current change on it? Think about it, my dear warriors. Basically, you are having a battery of sorts like this, and here you have a metal, here you have a metal, and this is basically constant, and you have basically light falling onto it. Wavelength is changed. How do you think the current in the circuit is going to behave? How do you think the current in the circuit is going to behave? Yes, think about it. Photoelectric effect can only happen. Photoelectric effect can only happen when the wavelength of the light is less than lambda naught, and the photoelectric effect will not happen basically when the wavelength of light is more than lambda naught. That is your threshold. So where is such an option? I think only D for, yes, Diksha ma'am, Dr. Delhi Ames. Yeah, that is the only one which is their option. Remember, I told you graphs are important and those questions do come. Okay, it is not B. See guys, it is not frequency. If it was frequency, then it will be correct. I think some of you said that. It is always confusing because when wavelength increases, energy decreases. Understand? So actually these are less energy photons. So photoelectric effect will not happen. So when wavelength is less, energy is more, so photoelectric effect will occur. When wavelength is more, it will not occur. I hope this is absolutely very, very clear. Absolutely very, very clear. Understood till this point? Yeah. So this was your lambda naught. This was your lambda naught. Nothing else will match. That is option D over there. Let's go to the next question on your screen. What does it say? The work function of a metal is 4. The emission of the electrons of 0 velocity for the metal surface of wavelength of the incident radiation should be. Guys, what is the meaning of this word or this phrase 0 velocity emission? Means just emitted. It is just emitted, and if it is just emitted, that means it is nothing but work function that we are talking about. The scenario of work function where the energy of the photon is just the work function. So that is given to be 4 electron volt. Energy of the photon is given by 12400. I can see Armstrong. The moment I see Armstrong and I see a dot over there, I remember there is one extra 0. 1240 and extra 0. Armstrong has that bulb, that 0 on the top. So put that extra 0 divided by lambda. But this lambda will obviously be in Armstrong. This is in electron volt. This is in electron volt. So lambda will be 12400 divided by 4. How much will it be? 3100 Armstrong. Just check it out. C for Captain Shreyas. Yes, it is. Yes, it is. C for Captain Shreyas. Very good, Abhisha. Thank you for all the love and hearts. Means a lot. Thank you so much. Yes, Rishita. Very good. Very good, Nishala Sanvi. C for chocolate. C for Captain Shreyas. Thank you, Chaitu Diaries. Pratibha. Very good. Govinda. Very good, Penchala. Awesomeness, Anju. Awesomeness. Awesomeness. Sushi Mama is also here. Very good. Nice to see you back. Sheshadri. Very good, Meghna. Very good. Very good. Moving on to the next one on your screen. Photons of certain frequency are falling on a metal surface for which the threshold frequency is nu naught. Then all the electrons have the same energy. The electrons have a distribution from 0 to something. Most energy is h nu. Average energy is h nu naught. There was a slide which talked about it. I hope you remember that. Just go back a little here. Maybe, where is it? Where we spoke about this? This one. The photoelectrons, look at this. The photoelectrons have different kinetic energies from 0 to k max. From 0 to k max. I just gave it to you in notes. So my notes are very important if you think. K max is E photon minus 5. K max, take that 5 over there. E photon minus 5. So let's go back. So what is K max? K max is energy of the photon minus 5. Energy of the photon is h nu. Work function is h nu naught. So all the energies will be there from 0 to K max. From 0 to K max. Where is such an option? Basvasaurus sir. Basvasaurus sir. Yeah, is the answer. Biology, botany, Basvasaurus, Basva sir. Yes, very good. Nishala, Pratibha, Jana, Govinda, Jensila. Awesome, Rahul, Krishna. Very good, Vaibhu. Very good, very good. Excellente. Proud of all of you. Going to the next one. What does it say? It says, when light of frequency 2 nu naught is incident on a plate, the maximum velocity of the electron emitted is v1. When the frequency of the light is increased to 5 nu naught, maximum velocity becomes v2. Then the ratio of v1 by v2, this is like the first question only, nothing more. See, general equation is energy of the photon is work function plus maximum kinetic energy, half mv square. That is what it is. Let's apply it 2 times. Let's apply 2 times. When the light of frequency 2 nu naught, that means f is 2 nu naught, falls on a surface whose work function is not given, threshold frequency is given. So threshold frequency is given. So that means work function will be h nu naught. The kinetic energy is not given, but the maximum speed is given. The maximum speed is v1. So half m v1 square. From this half m v1 square, 2 minus 1 is 1. So it will be h nu naught. That is the first part. Second time, when the frequency of the light is changed to this much, speed is this much. So h into 5 times nu naught is h nu naught plus half m v2 square. I'm just using this equation, but the energy of the photon will now be different. Work function will be same. Speed will be different. So what will half m v2 square be? Subtract 5 minus 1 is 4. So 4h nu naught. So now obviously take this and take this, and what is it? The ratio of v1 by v2 is asked. That means divide both of them. Divide this with this, v1 by v2 whole square. So v1 by v2 whole square will be h nu naught by 4h nu naught. H nu naught by 4h nu naught, which is 1 by 4. So v1 by v2 will be root of 1 by 4, which is 1 by 2. 1 by 2 is option A. This was in NEET 2018. Such a straightforward question, common question, direct question. Is that clear, everyone? Awesome, Abhi, Nishala, Tommy, Swadhana, Krishna. It's your Lisa. Very good, Pratibha, very good, Sheshadri. Moving on to another question. This was also a very popular model of question. Two identical photocathodes receive light of frequencies blah blah. The moment people saw photocathode, sir, what is this photocathode? Arey, nothing. Photo means light, cathode means the plate, the metal on which the light falls, receiving end, that's all, nothing else. Okay, the velocities of the electrons, are v1 and v2. What are they related with? Guys, don't you see this is very much similar to the previous model of the question? Instead of ratio, they have asked the difference. So just write energy of the photon, which is hf1, will be work function plus half m v1 square. Next time, hf2 will be work function plus half m v2 square. What you do now is basically subtract the two, so that 5 and 5 will get cancelled. So hf1 minus hf2 will be half m v1 square minus half m v2 square. H is common. f1 minus f2 is equal to half m is common, v1 square minus v2 square. What are they asking? v1 square minus v2 square, right? So from here, take 2 on the top, h is on the top, f1 minus f2 is also on the top, and divide by mass, you will get v1 square minus v2 square. That's it. That's it, guys. So we have got the answer 2h f1 minus f2 by m. Where is it? Option number A. A for AIMS. A for AIMS. Wow, looks like so many of you are going to AIMS now. Very good, Sanvi Parsan. Mr. Nobody, awesome. It's your Lisa. Very good, Lavanya, Nishtala. Yes. Very good. Cool. So I hope you guys have got confidence now on photoelectric effect and photons and wave particle duality. Are you ready to get that same confidence on atoms and spectra? We are moving really amazingly well, solving the questions and understanding the concepts. Quickly drink some water. Water break. And I'm advertising Vedantu also by drinking it from the Vedantu water bottle. See? Nice, right? Oh, by the way, there are some amazing merchandise from Vedantu on the Vedantu store. You're going to buy cool Vedantu shirts and all the cool merchandise is there on the Vedantu store. Just search for Vedantu store on Google also, you will get it. Okay, all the warrior Pandus assemble. Oh, you're fasting? Oh my god. Okay, no issues. What time will the class continue? So what is the time now? It's almost 4:40. So 1 hour for this, maybe around 7:30, I'm guessing, around that time. Yeah, close to that. Okay, so that is what I'm guessing, 7:30, 6:30, anywhere between that. Okay, cool. So let's begin, guys. Atomic structure and spectrum. Now, in the initial part of the chapter, you have the different models of atom which you have also studied in chemistry, like from your Dalton's model of atom, to then your Thomson's model, which is your watermelon or cake pudding model, to then your Rutherford's model, which had your gold foil alpha scattering experiment, to then the Bohr's model, and then you have the molecular orbital theory. Okay, this is how the flow of different theories are. Now, I would say just read through this Dalton's model, Thomson's model, and Rutherford's model. Read basic theory from your either Tattva module or from NCERT. That should be sufficient. Tattva is your Vedantu coaching material. They should not ask any questions from here, but just on the safety side. Okay, if you are aiming for 700 out of 720, then you can read it. Otherwise, if you are targeting 650 also or 600 also, there is no need. Why did I say that? They should not ask the questions because they are not there in the syllabus right now, only for that. Okay, main thing what you should know, MOT is also not there in the syllabus. So the only thing that you should be focusing mainly on is the Bohr's model. Just to give you a heads up of what was Thomson's and Rutherford, so that you remember it and probably you find it easier. See, Thomson's model is where, imagine a watermelon. Watermelon has the red part and the seeds which are embedded in it. The red is basically your positive charge. The seeds are the negative charge. So Thomson said the atom is neutral body. There is no excess positive or negative charge. So the positive charge is spread throughout the atom, and the seeds are the electrons which are spread at regular intervals, small things, and they neutralize the total charge. And the positive charge and the negative charge, attract and repel each other and keeps the atom stable. That's what he said. And when electrons are plucked out of it, it is very easy to pluck the seeds from a watermelon, and that's how conduction of electricity happens. But he was not able to explain atomic spectra and why the atom's orbits are there and all those things. So he failed in many ways. Then came Rutherford's model, where he found that atom's mass is not spread everywhere like a watermelon. Rather, the red part, which he thought was positive, is actually there only in a very small region called as the nucleus. Nucleus held most of the mass of the entire atom, and most of the atom was actually empty. And the seeds were not actually at rest, but in fact they moved around the nucleus by the electrostatic force which was producing that necessary acceleration for circular motion. Okay, so basically, Rutherford led to the discovery of nucleus and atom's emptiness and how, the electrons are in the orbits. But he was not able to explain why the electron is stable, because if it is in the orbit, it is accelerated and it will emit electromagnetic radiation by Maxwell, why atomic spectra is there, and so many other things. So again, Rutherford's model also had some flaws in it. So then Bohr came up with his own model, which overcame the flaws in all these people, and it explained it in a much better way. Like it was able to explain atomic spectra, calculate the radius of the orbits, calculate the energies, speeds, and so much more. And it satisfied the positives of these models. But even Bohr's model fails at a later stage because it does not satisfy Heisenberg's uncertainty principle, or even it does not calculate the radius or energies for higher atomic numbers. So it was not able to explain many things of probability, Heisenberg's uncertainty, and explain many other effects for higher atomic numbers. Even there is an effect called as Zeeman effect, which electric and magnetic fields cause splitting of atomic spectra and some crazy things happen over there. Even that effect it was not able to explain. So that is why Bohr's model was overthrown, and then we came to molecular orbital theory, which is the latest theory that we have. Okay, but we are going to focus our attention mainly on Bohr's model. Is that okay? Is that okay? All right, all right. So I think I just told what is the difference between the nucleus of Thomson. According to Thomson, nothing like nucleus. The entire mass was distributed like a watermelon, and electrons were embedded and electrons were stationary. But Rutherford said, no, the mass is not spread. It's concentrated in a teeny mini region. It's empty, most of the atom. Electrons are not at rest. They are revolving by the electrical force, which is like the centripetal force to rotate it in a circular motion. That's the major difference. Is that okay? I hope this is clear. Right. Shall we go ahead? Shall we go ahead to the Bohr's model? So what are the assumptions of Bohr's model? What are the assumptions of Bohr's model? According to Bohr's model, what happens is basically the electrons revolve around the positively charged nucleus in something called as the stable orbits, by the electric force providing the centripetal acceleration, by providing the necessary centripetal acceleration for the circular motion, of the electrons. That is number one. Next thing is that these orbits are stable. These stable orbits, also called as stationary orbits, have fixed energies, so the electrons don't lose energy by radiation. By radiation, they do not lose any energy. These are stable orbits, or also called as stationary orbits. Keep this in mind. Now, next thing is that when electron jumps to a higher energy orbit, it absorbs a photon whose energy is same as the difference of the energies of the orbit. Energies of the orbits. We'll explain this in a bit, but these are the postulates. Also when an electron de-excites to a lower orbit, instead of absorbing, it will emit orbit. It emits a photon whose energy is same as the difference of energy between the orbits. In fact, the mathematical way of writing it is the energy of the photon is the difference of the energy of the orbits. This is the mathematical way of writing it. The last one is the angular momentum of an electron in a stable orbit is basically integral multiple of h by 2 pi. Okay, is integral multiple of h by 2 pi. So L is basically nh by 2 pi. So this is another formula which you should know. H is your Planck's constant. N is also your principal quantum number. N is equal to 1 is basically your K shell. N is equal to 2 is your M shell. Is your L shell. N is equal to 3, M shell. N is equal to 4, N shell. So it basically represents what? Your principal quantum number. Principal quantum number. That is what it basically represents, the value of N. K shell, L shell, M shell, right? That is what it is basically going to tell me all about. So all these formulas are very, very important. All these formulas. These are the major things about Bohr's model that you must be definitely aware of. Now what you should also be aware of is the drawbacks or basically the flaws in Bohr's model. The flaws in Bohr's model also. Flaws in the Bohr's model. Number one is basically Heisenberg's uncertainty principle. Heisenberg's uncertainty principle, where you cannot find the momentum and the position simultaneously. So if you know where it is, you don't know what is it doing. If you know what it is doing, you don't know where is it. So where and what it is doing cannot be known to you simultaneously. That is the problem with Heisenberg's uncertainty. Second problem, it is not applicable for atoms of multi electrons. Meaning, if you think about lithium or zinc or tin, they have multiple electrons. It is not applicable. You will see it does not consider the electrical repulsion between multiple electrons and all that. Single electron is there, okay. Multiple electrons are there in the orbits, not applicable. It was not able to also explain Zeeman effect, which is basically the splitting of the spectra in electromagnetic fields. It was not able to explain why the atomic spectra splits. Okay, that is basically your Zeeman effect. That's all you should know. Okay. Yes, we'll be giving a short break after some time. Definitely. Don't worry. Yeah, cool. Okay, so these are the main things about about basically Bohr's model, the positives as well as the negatives. So what happens is, when you derive all the formulas, you show the nucleus like this. The nucleus has protons which is equal to the atomic number. So you will have multiple protons over here, and then you will have this particular electrons which are revolving in orbit. But remember, Bohr's model is valid only for single electron. It's only valid for single electron atoms. So this is the radius. Maybe the electron has some velocity over here, and obviously there will be a force acting towards the center. That is the electrostatic force, and that is giving the necessary centripetal acceleration. The charge on the nucleus will be obviously plus ZE. The charge on the electron will be minus E. So if you apply Newton's laws of motion, you will see that the force is equal to mass into acceleration. The force is nothing but your 1 by 4 pi epsilon naught. Charge 1 is ZE, the other charge is E, divided by the distance, which is r square. This is equal to mass into centripetal acceleration is v square by r. This is one equation. And the other equation that we have already seen is angular momentum is nh by 2 pi. Angular momentum is mass into velocity into r, so is equal to nh by 2 pi. This is your second equation. This is basically your second equation. From 1 and 2, using both of them, from equation 1 and 2, what you get is very important. The radius comes out to be proportional to n square by z square. Okay, you will get it basically proportional to n square by z square, and the velocity you will get it proportional to your z by n. Okay, so the derivations are not so important. Main thing is you should know, okay, it leads to, these relationships. These particular relationships. That's all. Is that okay, my dear warriors? Just one second. Okay, so velocity is proportional to z by n, and r is proportional to, just one second, sorry guys, this was just z, I by mistakenly said z square, n square by z. These are the two major things which you should know. Now, if you put n is equal to 1, if you basically put n is equal to 1, you will get the radius of the first orbit. So for n is equal to 1, for hydrogen, the radius that you get is basically 0.529 Armstrong. This is also called as the Bohr's radius. Keep this in mind. This is also called as the Bohr's radius, 0.529 Armstrong. Harni, yes, n square by z. I by mistakenly had put it as z square, my bad, sorry. Yeah, I changed it later on. Okay, so n square by z is proportional to that. Velocity is proportional to z by n. N is equal to 1 for hydrogen. You will get the radius as 0.529 Armstrong. Another thing that you will get is the kinetic energy, which is half mv square. The potential energy, which is minus 1 by 4 pi epsilon naught Ze into E divided by R square. Why minus? Because the charge on the electron is negative. K Q1 Q2 by R. K Q1 Q2 by R is the energy. Adding these two, you will get the total energy. You will get the total energy. When you do all the mathematics and find out, you will see it is minus 13.6 Z square by N square, but in electron volt. This is a major formula which you must know. This is a major formula which you must definitely know. Minus 13.6 Z square by N square electron volt. And you also will find out that this kinetic energy is actually the negative of this total energy, and this potential energy is nothing but double of this total energy. This was also there in satellite theory. This is also valid for atomic structure. Very, very important. Kinetic energy plus potential energy is the total energy. Kinetic energy plus potential energy will give you the total energy, and it happens that the kinetic energy is negative of the total and potential is double of the total. This is something which you should definitely remember. Till this point it is clear? Till this point it is clear? Everybody with me? Awesome, awesome, awesome. Very good. Let's go now to the next point. Let's now go to the next point, guys. Ready for this? Okay. Now, if you draw energy levels for any atom based on this particular equation. You choose any atom, that means atomic number is decided. You show energy levels, that means you choose different values of n. L shell, K shell, M shell, like that. You will see different energy levels will be there. So, if I show those energy levels, starting from n is equal to 1, which is basically your K shell, then let's say n is equal to 2, which is your L shell, then n is equal to 3, which is, let's say, your M shell, then n is equal to 4, which is N shell, and so on and so forth. You will see that the lines keep on coming closer, and after a point they come very close as n tends to infinity. The gap keeps reducing. If I actually tell you what are these lines going to represent, why am I showing it like this? This is lower energy. As I go up, it is higher energy. When the electron is here, lower energy, it goes up higher and higher energy. Here, the energy will be minus 13.6 electron volt. This is for Z is equal to 1, that is hydrogen. For hydrogen. Obviously, for helium, you will have to use a different value of Z. For lithium, different Z. For any other atom, you will have to use a different value of Z. Correct? So, here, if you substitute different values of n is 1, Z is 1, you will get 13.6. Z is 1, n is 2, 13.6 by 2 square, 13.6 by 3 square, 13.6 by 4 square. You will get the different energy levels. You will get the different energy levels. Like over here, you will get this as minus 3.4 electron volt. How did you get this? This is basically minus 13.6, Z was 1, N was basically 2. Similarly over here, minus 13.6 into Z was 1, N was 3. So 3 square. Did you get it? That is how you get the different energy levels. So after 3.4, I think you will get it as minus 1.5 electron volt and so on and so forth. In the end, you will get 0 electron volt. In the end, when n tends to infinity, you will get 0 electron volt. Is this clear? Awesome. Now, if till this point things are understood, what will the energy needed be if you want to take an electron from here to over here, basically infinity? Electron was at the lowest possible energy. You take it to n is equal to infinity, that means it is free. So the energy which you need will be this to this, the change will be how much? 13.6. 13.6. This energy is also called as the ionization energy. This is also called as ionization energy. So in order to ionize it, in order to ionize, from the lowest state, that is from the ground state, from the ground to the free state, from the ground to the free state. That is the meaning of ionization. The ionization energy will be exactly the positive value of this 13.6 electron volt, meaning you forget the minus sign. So it will be 13.6 Z square by N square. 13.6 Z square by N square. The energy required to free it completely. Make sense? Yep. Very good. So this is the energy required to chuck it out of the atom. It is completely free. Understand that. So here it is completely free. This was the ground state. This was the ground state. Now imagine any two levels of energy. Let's say there is an electron here and it jumps to over here. It jumps to over here. Maybe this energy is EI, this energy is EF. It jumps from here to here. When can this happen? This can only happen if there is a photon which is absorbed. If light is basically absorbed, then basically I will say it gets excited. It gets excited to a higher energy level. Same way, imagine if that same electron goes from this to this, it gets de-excited. It gets de-excited. It gets de-excited. And in this process, what do you think will happen? In this process, it will emit. It will basically emit a photon. It will basically emit a photon. So the energy of the photon, can I say it is nothing but EF minus EI? EF minus EI as per Bohr's model, as per Bohr's hypothesis. As per Bohr's hypothesis, correct or no? Very good. And this EF and EI values, I can write it like this. Let's say this is N1, this is N2, N3 like that. Maybe this is N2. N1 and N2 could be any numbers. 1, 2, 5, 6, 1, 8, 3, 5, 3, 10, 7, 20, anything. Some levels, just like we had over here. 1, 2, 3, 4, 5, 6. This and this, this and this, this and that. Anything. It could be any numbers in general. So can I not say this is nothing but minus 13.6 electron volt? This is your Z square by N1 square, or I would say N2 square, minus 13.6 E Z square by N1 square. Do the math and you will get 13.6 E Z square 1 by N1 square minus 1 by N2 square, and the energy of the photon over here, is nothing but 1240 electron volt, and then you will have lambda if it is in nanometers like this. Solve all these things and you will finally get 1 by lambda. Forget nanometers. In general, what you get is some constant. You will also get Z square. You will get N1 square, 1 by N1 square, and 1 by N2 square, the subtraction of it. This is also called as the Rydberg's formula. This is called as the Rydberg's constant. Rydberg's constant, right? Which is 1.1 into 10 to the power minus 7, right? So that is what your Rydberg's formula looks like. This is the wavelength of the photon which is either absorbed or which is emitted based on the transition which happens. based on the transition which happens. Is that clear? Everybody with me on this? Awesome. One second. Who are these students who are chumma chatting here and there? Come on guys, concentrate on the class. Yeah. So lambda is the wavelength of the light which is emitted or absorbed, and N1 and N2 are the numbers of the shells from where the transition happens. R is your constant, Z is your atomic number, Rydberg's constant also I have given to you. Okay, very good. Now, depending on where the transition happens, you have different names given to those wavelengths. So let's say this is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, and so on and so forth, like that till infinity. This is 1, 2, 3, 4, and like that till infinity. If by chance the transition is happening from the higher orbits to n is equal to 1, to n is equal to 1, that means something like this. This is called as the Lyman series. Transition is happening from any higher orbit to the lowermost orbit, which is 1. That is called as the Lyman series of the wavelength. Out of all these wavelengths, who do you think has the highest wavelength? Logic is simple. See, the energy difference is the energy of the photon, of the light. Energy of the photon of the light is hc by lambda. So that means the one which has more lambda has less energy difference. Less energy difference has more lambda. That means this lambda is the highest. And the one which has large energy gap has low lambda. Large energy gap has low lambda. So lambda is the least from infinity to 1. This is the longest wavelength from here to here. And this is the shortest wavelength from here to here, because energy is inversely proportional to lambda and directly proportional to the frequency. Now, the next series that you get after Lyman is nothing but Balmer, that is till n is equal to 2. Till n is equal to 2. N is equal to 2. Exactly. This is called as your Balmer series. In the Balmer series, who has the shortest wavelength? The one which has highest energy gap. So this has the shortest wavelength and this has the longest wavelength from 3 to 2. From 3 to 2 is the longest. Lyman, Balmer, Paschen, like that, P fund, bracket, many series are there. Till here is enough. Till here is enough. Lyman, Balmer, Paschen, right? P fund, bracket, all those things are there. All those things are there. You get many series. Okay? Is that here? So in your NEET syllabus, Lyman, Balmer, Paschen generally is more than sufficient, but P fund and bracket is also there. I have very little space, but I'll just put it over here. P fund and then lastly bracket. All these series are there. Okay? This is called as your atomic spectra. This is called as your atomic spectra. Why is it so important? Is because for a given atom or an element, this spectrum has unique wavelengths, just like your signature. If you use hydrogen, some lines are there only in hydrogen in a peculiar order. If you use lithium, it is different. If you use iron, it is different. So looking at these wavelengths, one can identify which element is actually present inside. So that is why atomic spectra is the signature of an atom, because they are very unique lines, and that certain wavelengths in a certain order are only there in certain elements. Is that clear? Okay, very good, awesome. So that is mainly what is there in this particular part of the chapter, which is your atoms. That is the Bohr's model, which I told you. You should know about angular momentums, the relationship, and the flaws of Bohr's model. How is radius and velocity related to each other? Z and N. Energy, kinetic energy, potential energy, and also the ionization energy, the energy level diagrams, the wavelengths which is going to be absorbed or emitted, and the atomic spectra. Now there is one more thing though, which can be asked sometimes. If this is the nucleus, which has a lot of protons and neutrons, and the electron is revolving around this orbit like this, electron's orbit is there like this. Because the electron is in motion, because the electron is in motion, it does have momentum. And anything which has momentum has a wavelength basically of the matter wave. Remember wave particle duality? It definitely has a D Broglie wavelength. Now, if you put the D Broglie wavelength of that electron like this on that orbit, like this, you will get exactly n number of D Broglie wavelengths. What is that n? Principal quantum number. This is a very, very important thing which you should know. Exactly n number of D Broglie wavelengths you will get in that entire orbit. That means n times of lambda will be equal to the circumference. What is the circumference? 2 pi r. And this will be basically n times of lambda. Very, very important thing. This r can be also written down as r naught into, remember, n square by z, right? What is r naught? The radius of the first orbit, or you can just put r1 over here, that is also okay. So you can put it as r1, which is 0.529 angstrom. This also is fine, one and the same thing. Radius of any nth orbit is proportional to n square, inversely proportional to z. So this is also a very, very important thing which you should know. N times lambda, n times will be circumference. Circumference is 2 pi r. R is the radius of the orbit. Radius of the orbit is proportional to n square, inversely proportional to z. Cool? Very important. Okay, great. Awesome. Let's move on to the next one. And here it comes. Why is the answer already there? I think it was supposed to be here. Okay. So guys, when an electron transits from 1 to 2, then the speed will become how many times? I know you guys saw the answer, but let's see how many of you are active on the screen. If the electron goes from n is 1 to 2, then what will happen to the speed? Remember, speed is proportional to z by n. So speed is inversely proportional to n. So if this value of n goes from 1 to 2, it has become 2 times. So velocity will go from 1 to half. So won't it become half times, guys? When the electron transits from 1 to 2, the electron's speed will basically become half. I think the answer is there on the next slide. Yeah, answer is there on the next slide right over here. Yeah, I think that was the answer for some another question. That another question was over here. When electron goes from 1 to 2, the radius will become how many times? From 1 to 2. Now we all know radius is proportional to n square. So think about it. If n becomes 1 to 2, that means it has become doubled. 2 square means 4. So the radius will become 4 times into 4 times. So the radius will become 4 times. The question here was of radius. Definitely it will become 4 times. And this one will become half because this was for the speed part. Next one. When an electron goes from 1 to 2, how many times will the energy become? N goes from 1 to 2, what will happen to its energy? Energy is minus 13.6 z square by n square. N square is there below. So if you make this n 2 times, the square of it will become basically 4 times. So it has become 1 by 4 times. It has become 1 by 4 times because n square is there in the denominator. So this will also become 1 by 4 times. So 1/4 of the time should be the answer, which is option C. Which is option C. Yes, very good, very good, very good. Option C is the correct. Very good. Awesome, awesome. Shall we go ahead to the next one? Shall we go ahead to the next one? Here we go. Okay. The kinetic energy of the ground state electron in ionized helium is, in ionized helium. Helium, first of all, what is the value of Z? It is basically 2. Ground state, meaning N is equal to 1. The kinetic energy is asked. Kinetic energy, remember, is the negative of the total energy. The total energy is minus 13.6 z square by n square. Minus minus becomes plus, so it will become 13.6 z. Z is basically 2, so 2 square by n. N is nothing but 1. So how much will it be? 13.6 multiplied by 4. Oh, come on. It should be 54.4 electron volt. How many of you wrote the answer as option A? Very good. If you wrote the answer as A, perfect. Perfect. Option A, Nishala. Pirarsan, Per. Wow, what a name, yeah? Yep. Very good. Very good. Very good. Keep it up. Moving on to the next one coming up on your screen. Here it is. What does it say? The D Broglie wavelength of an electron in the second orbit is how much? Where R0 is the radius of the first Bohr orbit. Okay, let's try to think about it. The D Broglie wavelength of an electron. I think we just studied some theory regarding D Broglie wavelength of an electron orbiting. We just studied n lambda, n times of lambda is the circumference. We just studied that. So maybe we have to use that over here. So let's use that over here. So n times the wavelength is the circumference. And the circumference of a circle is 2 pi radius of the nth orbit. Radius of nth orbit is what? Proportional to n square by z. So it will be R0 into n square by z. But this is the Bohr's radius. So basically we are talking about hydrogen, for which z is 1. So z is basically 1. So n into lambda is essentially this. Can you see nn will get cancelled? Lambda will be nothing but 2 pi R0. 2 pi R0. Where is it? B. Option B, guys. Right? Yeah, I think the answer marked over here was wrong. Yeah, the answer is 2 pi basically R0. But I think though they have asked n is equal to 2. Oh, my bad. N is basically 2. N is basically 2. So put 2 over here. So what will this become? 2 square is nothing but 4. 4 into 2 is nothing but 8. So it will become 8 pi R0. 8 pi R0. That should be the answer. 8 pi R0. Yes. So I think none of the options are matching over here. Maybe there was a misprint in this particular thing. So forget this. Just forget this. It's the second Bohr's orbit. So second Bohr's orbit means n is equal to 2. So when I put 2, 2 square, and this is 2 pi R0 over here. So lambda will be equal to 8 pi R0. That should be the answer. Is that clear, my dear warriors? Is that clear, my dear warriors? Perfect. No, none of the options will match over here. None of the option. No option will match. Okay. Chalo, let's move on to the next one coming up on your screen. In the following atoms and molecules for the transition from 2 to 1, this spectral line of minimum wavelength will be produced. Spectral line of minimum wavelength will be produced for which of the following? For which of the following? Yes. Oh, did I not cancel n? What is wrong with me? I think I need a break. Sorry guys. Sorry. I'm so sorry. Thank you for pointing it out. What did I just do? N and this N will get cancelled. N and this N will get cancelled. So what will be left over here will be lambda is equal to 2 pi r naught into N. So the value of N that I will put will be second Bohr orbit is 2. 2 2s are 4. So 4 pi r naught. So that is lambda. That is option C. Yes, perfect. No issues at all. Cool. Thank you for pointing it out. Yes, C for Capto is correct. Yes, we had to cancel that N. Moving ahead to the next one. In the following atoms and molecules for n is equal to 2 to n is equal to 1, the spectral line of minimum wavelength 1 by lambda is r z square 1 by 1 something square 1 by something square. This is 1 by 1 square minus 1 by 2 square. Where will you get the lambda minimum? If this is low value, minimum value, that means this ratio will become big. That means z square will become large. For whom is z more? For whom is z more? Hydrogen, deuterium, both of them z is 1. This is helium, z is 2. For lithium, z is 3. So the one with highest z has lowest lambda. So hence the answer should be lithium. The answer should be lithium. Is that clear, my dear warriors? Why the answer is lithium? Very good. Awesomeness. Moving on to the next one. The ionization energy of an electron in the hydrogen atom in its ground state is 13.6. Yes, we are knowing that. Atoms are excited to higher level to emit radiations of 6 wavelengths. What is the highest energy level? Okay. Now, think and tell me, guys. If these are the energy levels, imagine there is an electron over here. How many different transitions can it undergo to de-excite itself? It can go from here to here. It can then go from here to here, or it can directly go from here to here. So basically 3 wavelengths come when your n is equal to 3. When your n is equal to 3. Imagine now there are even more orbits. I take an electron here. What are the different possible outcomes of the transitions that can occur from this shell? From here to here, then from here to here, then from here to here, then from here to here directly, and then here to here, or from here to here directly, or once it has landed here, then it goes from here to here. 1, 2, 3, 4, 5, 6. 6 possibilities are there if it starts from basically 4. If it starts from 4. So now think, in general, if this is n, how many possibilities are there? How many possibilities are there? For 3, it is 3. For 4, it is 6. For 5, it is how much? What is the answer, guys? The general formula which comes for this is n into n minus 1 by 2. Check this out. 3 into, just apply this, 3 into 3 minus 1 by 2. 3 minus 1 and 2 cancels, answer comes out to be 3. Here, when you put 4 into 4 minus 1 by 2. 4 minus 1 is 3. 3 into 4, 12. 12 divided by 2 is 6. That's how you get it. So that is the general answer. So here, the atoms are excited to an energy level and you get 6 different wavelengths. You basically get 6 different wavelengths. So the final answer is 6. What is the value of n going to be? What is the value of n going to be? Obviously, the value of n is going to be 4. The value of n is going to be 4. So option B should be there. Yeah, option B is the correct answer. Got it? This is general formula. Yeah, definitely. We are going to have a break in just few more minutes. Just the last few questions to complete atomic spectrum now. Yeah. Come on guys, last 1 or 2 questions and then we are going to have a break. The total energy of an electron in an atom of orbit is this much. the kinetic and the potential energy. Direct question, guys. You should be able to solve this NEET 2019 question. Kinetic energy is negative of total. So it will be negative of minus 3.4. So it will be directly 3.4. So either it is here or it is here. What about the potential energy? It is double of the total. So it is 2 times of minus 3.4. So it is minus 6.8. So minus 6.8 is only there here. So option D should be correct. Yes, option D is correct. D for doctor. Very good. Awesomeness. Moving on. Ratio of the wavelength of the last line of Balmer to the last line of Lyman. Last line of Balmer. Lyman, Balmer. Balmer is n is equal to 2. Last line means from n is equal to infinity to n is equal to 2. Similarly, the last line of Lyman. Lyman means n is equal to 1. Last line means n is infinity to 1. So for Lyman, the wavelength will be given by Rydberg's constant 1 by 1 square minus 1 by infinity square, which is r into 1 by 1 minus 1 by infinity is 0, large number. So in the denominator we'll make it 0, so it will be r. Similarly over here, 1 by lambda of Balmer will be Rydberg's constant 1 by 2 square minus 1 by infinity square. So it will be r into 1 by 4 minus 0. So it will be basically r by 4. So once I got this, I'll just divide them. I'll just basically divide them. 1 by lambda Lyman by 1 by lambda Balmer will be r divided by r by 4. Lambda b will go on the top. Lambda L will go below. Lambda L will go below. 4 goes on the top, RR cancels. So 4:1 should be the answer. Option D. Option D, yes, option D is the correct one. Option D is the correct one. Very good. Excellent. Excellent. Got it, guys? These are the standard models of question. You can see these are also PYQs. Yeah, perfect. Okay. So let's take a break after this now and we will meet after some time. But meanwhile, do not forget that the crash course for NEET 2024 has started. My first class is going to be tomorrow, yeah, Sunday. Earlier I had kept it, yesterday, but many students wanted to join today over the weekend. So that's the reason why I shifted the class on Sunday and they wanted to attend my first class live. So tomorrow will be my first class and you will also have other teachers teaching in this particular batch all the topics, and we will be also helping you with your preparation throughout the next few weeks. Okay, so make sure you enroll into this particular crash course. And the best part about this NEET crash course, it's in English. You have the best teachers, you get the soft material, you get the test series, you get the assignments. All India level mock test series is also a part of it. And not just that, you will also get this crash course for a very good price, just 999 rupees. Old price was 1999. Okay, so it is just 999 rupees. The link is there in the description box. Okay, just check that out. Right, so let's meet after a break. We'll just take a break now. It's 5:30, so break time. We will meet at 5:50 p.m. Okay, we'll meet at 5:50 p.m. Okay, I'll see you. I hope I'm audible and visible, everyone. The break time is over. Get back, get back, get back. Let me also put the message on the Telegram channel so that students are back. Yes, the break is over. We have completed atoms. We have completed photoelectric effect. We have completed wave particle duality and photons and atomic spectra. Yes. So let's begin. Let's begin. Okay. Just 1 second, let me get my chats properly. Okay. Yes, time to be back. Hello Tommy, hello Preeta, Krishna, welcome Meghna, hello Aimless. Is this session includes all the contents of modern physics? Is it enough concepts for learning? Yes, Preeta, it is. I think Preeta, you are only asking, sir, please complete modern physics here and there. So yes, all the necessary concepts in this particular video is going to be covered. Okay, so watch it. It includes all the chapters: atoms, nucleus, photoelectric effect, then your semiconductors and logic also. Cool. So let's begin with the next part, and that is your nucleus. Get ready, guys. Get ready. All right. So when we talk about the nucleus, the first thing that comes to our mind is it is bulky, it is at the center, it is very dense, and the space around it is empty, and electrons are revolving around it. And a nucleus is made of two things. One is the protons, and the second thing is the neutrons. Protons P, and of course the neutral particles N. The neutral particles basically N. Together makes the nucleus. So in fact, protons and neutrons are called as nucleons. They are called as nucleons. They are residents of nucleus. That's why nucleons. Like if I stay in let's say Bangalore, then I am called as a Bangalorean. If I stay in India, I am called as an Indian. Same way, if I stay inside the nucleus, I will be called as a nucleon. Correct? So the number of protons which are there is usually the Z, which is your atomic number, which decides your chemical property. So this is your atomic number. Then the number of neutrons which are there, it is also called as your neutron number. Together, if I add them both, what I get is capital A, which is atomic mass number. Right? That is your atomic mass number. So if two or more people have the same Z but different neutrons, they are called as isotopes. Correct? So if something has the same Z but different number of neutrons, they are called as isotopes. If there are two or more elements with the same number of neutrons, they are called as isotones. And if two or more elements have the total number same, have the total numbers of protons and neutrons same, basically atomic mass number is same. So same atomic mass number, they are called as isobars. Do remember the electrons revolve in orbits around them like this. Electrons are present in the orbits around them, right? So these are the orbits of the electrons outside. If you want to represent this element with this A and this Z, this is how you basically represent it. The atomic mass number is always put on the top. The element whichever is there, you will, let's say, call it as X. It could be hydrogen, helium, whatever. And the the proton number or the atomic number is usually put over here. Below. That's how you put it. So X is the element which we are talking about. That's how you represent it. Is that right? These are the basic things which you should know about a nucleus. Which is the basic thing which you should know about the nucleus. Amazing. Now, when we talk about a nucleus, the nucleus has an approximate radius, and the radius of the nucleus is approximately 1.2 into 10 to the power minus 15 meters into a raised to 1 by 3. A raised to 1 by 3. So basically the radius is proportional to a raised to 1 by 3 is the atomic mass number. This is something which you should be aware of. The cube root of A is what R or the radius of the nucleus is proportional to. Is that okay? This is one important concept. Now, you can also end up measuring the density of the nucleus. The density of the nucleus is the mass of the nucleus upon the total volume. Now, remember, proton and neutron have very similar masses. Proton and neutron, they have very similar masses. So, when we take a proton, the mass of the proton is approximately equal to the mass of the neutron. Is equal to almost the mass of the neutron. In fact, the charge on the proton is plus E, but the charge on the neutron is 0, right? That is what it is. So you will see that the total mass of the nucleus, because it is made of protons and neutrons, I can just say is nothing but total number of nuclear particles is A. The total number of nuclear particles is A multiplied by the mass of the proton. Makes sense, guys, everyone? Reason for this is because it is Z into MP plus N into Mn, but mass of proton and mass of neutron are almost equal. So it will become Z into MP plus N also into MP. Z plus N is nothing but A. So it will be A into mass of the proton. A into mass of the proton. I have taken it common. Z plus N is nothing but A. In the denominator, volume is basically 4 by 3 pi r cube. 4 by 3 pi r cube. Okay, no issues. So this will become 4 by 3 pi. Radius is this number into a raised to 1 by 3. Is some constant into a raised to 1 by 3. Now this whole cube should be there. The radius is this number, some constant into a raised to 1 by 3 whole cube. So 1 by 3 will cancel, and what am I left with? I am left with 4 by 3 pi constant cube into A. Do you see this A and this A is cancelled? This A and this A just got cancelled. So what are remaining? Mass of the proton 4 pi constant and 3. That means it is just another constant. So the density of all the nuclei are same. It's a very, very important outcome conclusion which you are getting over here. Is that okay? Everybody clear? Awesome. Let's go ahead. Now, we have talked about what a nucleus is made of, what are the different ways of which you write the nucleus, and then we have also seen the radius and the density of the nucleus. Now, how is it that inside a nucleus, protons which are positively charged, even though they might be repelling each other, like this guy repels this guy repels this guy is repelling this guy is also repelling this is also experiencing repulsive force here, repulsive force here, repulsive force here, repulsive force here. This guy is experiencing repulsive force from this, and this guy is also experiencing repulsive force here, then here, and here. This guy is also experiencing repulsive force like this, and like this. How is it that they are not flying out? It's only because of these neutral particles. Only because of these neutral particles. These neutral particles actually hold the proton together, and they also bind together. They also will bind together. So that is how it is able to hold the protons inside the nucleus. And that force which is there between neutron, proton, neutron, etc., that is not electric, it is not magnetic, it is not gravitational, it's a new kind of force. And that is called as the nuclear force. Nuclear force. Nuclear force. Nuclear force is going to hold the nuclear particles together. Nuclear particles together. Remember, it doesn't depend on mass or basically the charge. Even proton and neutron can attract, repel each other based on nuclear force. It is not dependent on, oh, the mass is more or mass is less. Okay, it is not dependent on that. It is a new kind of fundamental force. New kind of fundamental force in nature. Also, it is very short distance force. Very short distance force, typically of the order of femtometers, or basically 10 to the power minus 15th of a meter. In this range, it is very strong. Apart from that, it is not going to act. Also, it is the strongest force at the short range. Very important. Like gravity is a very long range force. Moon and Earth can attract each other. It's a long range, but it is very weak. Electromagnetic is slightly stronger, and it is acting at normal distances, few centimeters, millimeters, micrometers. Even lesser than that is nuclear, extremely short range and even more powerful. So you cannot experience nuclear force from here to here. No, very short distances within the nucleus itself. Okay, I hope this is clear. Super 6 Doctor series is over. So this is our block series, my dear friend. So concentrate on the block series. Super 6 series, long time. I don't know whether you are aware of this. It's over, long time back, everything done and dusted. Also, this particular nuclear force, if it doesn't depend on the mass and the charge, what does it depend on? It depends on the spin of the particles. Keep this in mind. So these are the most important things that you should know. Also, you should know it can be attractive. It can be attractive or repulsive. It can be attractive or repulsive, and act between, and it can act between proton, neutron, or even neutron and neutron, between any of them. That is how the the nuclear force can act. Okay. Dr. Sri, I don't think any biology chapters are pending. Even if it is pending, it will be done in the block series. So concentrate on the block series, my dear friend. Okay, so this is a block series where everything else, whatever is required, will be completed. Yep. Yeah. Yes, Krishna. Yes, it will be dependent on this. Perfect. Now that you understand this nuclear force, does this nuclear force result in some kind of energy which is being created or lost or being absorbed or anything? The answer is yes. Remember, whenever things are stable, energy is released. Imagine when you reach home, what do? You release your gas, है ना? You heave a sigh of relief. Same way, when things are together and stable, they release energy and they heave a sigh of relief. They are like, Abba, ayo, it's done. Release, release. So they release energy when they are stable. Okay, understand this. So you will see that there is some energy associated with, the nuclear particles being together, and we will call that as the binding energy. So let's see what this binding energy is all about. But before that, what happens when you have a mass and let's say somebody destroys the mass? Somebody destroys the mass. You will see that energy is going to be created. You will see that energy is going to be created. Energy is going to be created. Same way, imagine if somebody destroys the energy. Basically, somebody absorbs that energy. So energy is basically, I would say, absorbed or destroyed. If it is destroyed, then what will you get? You will get back the mass. Mass is going to be created. Mass is going to be created. This is basically called as Einstein's mass energy equivalence. Mass energy equivalence. Mass energy equivalence. This is Einstein's mass energy equivalence. Mass is destroyed, energy is created. Energy is destroyed, mass is created. And the relationship between them, very simple. If the energy absorbed or destroyed is E, mass absorbed or destroyed is M, E is equal to mc square. That's it. E is equal to mc square. M is the mass which is destroyed or created, E is the energy which is destroyed or created, C is the speed of light. As simple as that. I hope this is clear. Yeah, I hope this is understood. Okay, very good. So now that you understand that, okay, mass is somehow involved in energy creation or destruction, what has that got to do with nucleus? We'll come to it, don't worry. Usually, when the masses are very, very small, you don't use kg. Like you will not use mass in kg or in grams, you will use mass in a very different unit. Like when you measure gold ornaments, do you use kilograms of gold? I don't think anybody goes to the shop, shopkeeper, give me 5 kilos of gold. Unless you are very rich. You will ask gold in grams. So when you go at the atomic level, will you ask for the masses in grams? No. You will ask for the masses in, yes, atomic unit, AMU, correct. So you will need a new unit, and that is your atomic mass unit. Atomic mass unit, which is AMU, which is nothing but 1/12 the mass of your carbon 12 isotope. Now, till this point it is clear. Yeah, guys, please don't concentrate on other things, okay? Don't worry about spammers. There is some paid person from other institutes who will basically disturb the class and do all unnecessary things. So don't worry about all these things. Cool. So what is the value of this atomic mass unit, guys? What is the value of this atomic mass unit? It is nothing but 1.67 into 10 to the power minus 27 kg. If you substitute the mass over here, if you substitute the mass here, speed of light here, and convert it into joules, if you convert it into joules, electron volts, my bad, like this, the energy is equal to, you put 1 AMU, which is 1.67 into 10 to the power minus 27 into speed of light, which is 3 into 10 to the power 8. This will be in joules. You convert it into electron volts, so 1.67 into 10 to the power minus 27 into 3 into 10 to the power 8 divided by 1.6 into 10 to the power minus 19. The answer that you get will be in electron volt. This answer comes out to be basically 931 mega electron volt. So if you destroy one atomic mass unit, you will get 931 mega electron volt. Mega is 10 to the power 6, basically 10 to the power 6 electron volt. So in general, if mass is expressed in AMU, how many mega electron volts will you get? How many mega electron volts will you get? You will basically get the mass which has been destroyed or created into 931 mega electron volt. This is the answer. This is the answer. Is that clear, my dear warriors? Is this clear, my dear warriors? So if you destroy one AMU, you get 931 mega electron volt. If you destroy m AMU, you will get m into 931 mega electron volt. Yes. Yes, it is c square. I did not put c square. Okay, my bad. Yeah, put c square. Sorry. Yeah, c square. My bad. Yeah, c square we had to put. So this is the point. You have converted this into mega electron volt. And this is a very, very important conversion formula, because usually our masses will be in AMU and the energy will not be in joules or ergs. Usually it will be in electron volts. That is the reason why this conversion formula becomes very important. So now we know that mass destruction creation, energy destruction creation are related to each other. And we have seen this in the atomic level, in AMU and in electron volt. Okay, but what has that got to do with nucleus? How is that related to the nucleus? So let's have a look at it. Basically, imagine we have to make a helium nucleus. We have given the task of making a helium nucleus. What is a helium nucleus made of? It is made up of two protons and basically two neutrons. So let's say I asked for two protons, I asked for two neutrons, and I combined them together. I combined all these things together to make the helium nucleus. Two protons and two neutrons to get the helium nucleus. In this process, do you think the mass will be conserved? The answer is no. The mass won't be conserved. You will be like, sir, what? Really? Mass is not conserved? Will it be increasing or decreasing? The answer is, it will be decreasing. Some of the mass will get destroyed. Yeah. So when these protons and neutrons combine together, imagine the total weight was 1.729 kg. Maybe over here, the total weight will be 1.7284 kg. So do you see that there is a small difference of the mass? So there is a loss of mass in this. So when the mass is lost, what will happen? Obviously, energy will be created. So you will see energy is released. Energy is basically released in this process. Energy is going to be released because mass is going to be destroyed in this. The amount of mass destroyed in such a process is called as the mass which is defect. You are expecting some mass, but you are getting something else. So that is basically the mass defect. So in this case, the mass defect will be the mass of the total protons plus the total mass of the neutrons minus the mass of the nucleus. Minus the mass of the nucleus. That is nothing but your mass defect. If you multiply this mass defect with 931, you will get the energy which has been released. This energy which has been released is in the process of binding these particles together. Bind means together. You are bringing them together. That is why this energy is also called as binding energy. This is also called as binding energy. Hence, the formula for binding energy, just becomes the mass defect which is there into 931 mega electron volt. Mass defect which we found out into 931 mega electron volt. Is that clear, everyone? Very good, very good. So keep all these pointers in mind. Whenever a nucleus is formed, the mass is always going to be destroyed, and the destroyed mass converts itself into energy. That energy which is released in the binding process is called as the binding energy. Now, like I said, when you become stable, you release more energy. You become very happy and you release all that energy. So, is the binding energy released to how stable this nucleus is? The answer is not entirely. In fact, there is a term called as the binding energy per nucleon. Per nucleon, meaning the binding energy upon the number of nuclear particles. This is what decides the stability of a nucleus. This is what which decides the stability of a nucleus. How much energy is released per particle of the nucleus. And scientists have drawn a graph of this versus Z of binding energy per nucleon, and that graph looks something like this. It becomes maximum for iron. Okay, it becomes maximum for iron. That means it is the most stable nucleus. It is the most stable nucleus because it releases more energy for every nuclear particle inside of it. That is why it is most stable. Everything else is less stable than iron. So this is like the class topper. This is like the class topper, or somebody who has some attractive maybe game or maybe some nice toy, or I don't know, something like that. So everybody wants to be like iron. Everybody wants to be like iron. Yes. So if everybody wants to be like iron, what will these people who are having lower atomic number like hydrogen, helium try to do? They will try to combine together. They would want to become iron. When they combine together, that process is basically called as fusion. So a fusion process can make these nucleus more stable. But it is not easy. It's not like hydrogen will say, hey hydrogen, come, let's all meet together. Let's also find few more hydrogen and let's all meet and become a big nucleus like iron. It is not so easy. They'll be like, why should I come? Get lost. I don't want to come. You have to convince. It's like planning a trip with many friends, or planning a trip or planning an outing with many friends in the group. It will never happen. Imagine some 10-15 friends are there together. You want to go at one place, you'll be like, no, I don't want to go to this movie. I want to go eat outside. No, tomorrow I want to sleep. Tomorrow I have studies. It will never happen. But 2-3 friends means it will happen. So when these people decide to come together, it is very difficult. You have to force them, and this fusion happens under a lot of pressure. In the sun, the hydrogen combine together to become helium. So that is a fusion reaction which happens inside the sun under immense pressure and lot of high temperature. It's a forced process. And when they come together, they are like, oh, wow, it's so nice. All of us together, we have more energy per nucleon. But to bring them together is a task. Are you getting my point? Are you getting my point? Yes, exactly. The exact reverse happens over here. These are very heavy nucleus, like a big group. big group, 100 people friends group. Some people are there, I don't know. WhatsApp group, 100 people friends group. Ayyo, nothing will happen. Then you realize no point having 100 people. You break into smaller parts. You're like, okay, hey, you know what? All these people are mental. Let's make a small WhatsApp group separately. Happened or not? Okay, and then 10 people decide to be separate. Same thing, these uranium, thorium, plutonium, all these heavy elements, they realize, my God, being so bulky is of no use. So they decide to split. And when they decide to split, that is called as the fission reaction. That is called as the fission reaction. Is that clear? Fission is breaking, fusion is binding it together. Right. Now, in any fusion and fission reaction, it could be like, maybe example, X element is combining into or splitting into Y. 1 second. For fission, it could be like X is splitting into Y plus Z, and fusion can be like, I don't know, Y plus Z becoming, let's say, X. This is fusion, this is fission. In this process also, there might be some mass changes which are happening. Is that right? Here, this mass and this mass and this mass, if you add them, they might not tally. So there will be a mass defect. So that is why you will have some energy which is being released or which is being, absorbed. So that is the reason why you have a separate term over here, which is of energy, which is of basically energy, which is called as the Q value. Q value is nothing but the mass defect into 931 mega electron volt. So the Q value is basically the energy which is involved in a fission or a fusion process. In a fission or a fusion process. It is the mass defect into 931. If these masses are given, just subtract them and see which mass is more, which mass is less. Accordingly, you will understand whether energy is being released or whether energy has been absorbed. As simple as that. Yeah. How much weightage for this session? So Bhavdharini, I think at the start I forgot to tell this, but I think we have reached almost the end of this. So I will tell you about what is the weightage and what is the idea of the block strategy in a bit. Okay, don't worry. But till this point, I hope everything is clear regarding fusion, fission and all these things. Radioactivity has been deleted. Alpha, beta, gamma rays, which is a part of radioactivity, is deleted. So no need to study all those things which are there, okay, regarding radioactivity. Main things are right over here, okay. So I hope you have quickly seen through all these pointers. Now, before we go ahead, let me also tell you what I have done in these last few days and what we decided as a team. So, 720 marks we have split into basically 4 parts. This is block 1, block 2, block 3, block 4. Each block is how many marks? 180 marks. 180 marks. In that 180 marks, 120 is high weightage. 120 is high weightage. And sometimes you will have low weightage also. Let's say, for example, this is 60 marks, a low or basically medium weightage. Low or medium weightage. That is how each block has been split. Now, since every block will have 4 subjects: physics, chemistry, botany and zoology. So you basically take this 180 high weightage marks, 120 high weightage marks, and split it into 4 parts. So that will be basically 30 marks over here, 30 marks over here, 30 marks over here, 30 marks over here. That is the idea behind this. So every session we are basically targeting that 30 marks, 30 marks, 30 marks, 30 marks. So every block will totally give you 120 marks. Will give you 120 marks. Understood how this works? Same thing for block 2, block 3 and block 4. I hope this logic is very, very clear. Okay. Yeah. So 30 is bare minimum. 30 is bare minimum. This 30 can go till, this 30 can go till 40 marks also. So 30 to 40 marks is what we are expecting, from every block. Modern physics expect easily more than 5-6 questions with semiconductors and logic gates. Semiconductor guarantee 1 question, logic gates guarantee 1 question, 2 questions done over here only. Atoms, wave particle duality, nucleus and all these things, again you can expect easily 4 to 5 questions. So almost 7 questions to sure. 7 questions to sure. Sometimes they use alpha particle in magnetism. Sometimes they use proton by electrons, radius ratio in a magnetic field. So these basic things might be used in some other place. So you will see that 7 to 8 questions bear, like usually you can expect it. Usually you can expect it. Okay. So is this block strategy clear? So when you do it like this, it becomes very easy to complete the syllabus, and that is the approach which I use almost towards the end of the year when the exam is near. So students find this very beneficial. All right. So it's time to solve some questions, guys. Here is the first question on your screen. If Ra22688 nucleus is there, how many protons are there and how many neutrons are there? I just told you guys, whatever is there over here is basically Z is the number of protons. So 88 protons should be there, 100%, 88 protons should be there. That's it. And there is no such option other than that. So electrons also can be 88. Yes, 88 electrons also can be there, because if protons are 88, electrons will also be 88. But this option can't be true because atom is neutral. So if electrons are 88, protons also should be 88. So this is wrong. Protons should be 88. So option C is wrong. Option B only should be correct. And yes, option B is correct. But what about neutrons? That's not a problem. The number of neutrons is atomic mass number minus Z. So it is 226 minus 88 basically. So that will give you 138. So 138 neutrons should be there, which is option B. Got it, everyone? Yeah, B for biology. Welcome, Krishna. Very good, Pruthi. Puthuri Rishi. Okay. Great. Yeah, kinetic energy ratio. Yes. That's where it is used. Next question is density D of a nuclear matter varies with nucleon number as, I just told you. What about nucleus density? Right over here. The density of the nucleus is constant. We just derived it. So it is not even dependent on it. So it will be basically A raised to 0. It is just independent of it. Independent of it. Remember, density is a constant. It is a constant. So no other option will match. A raised to 0 is 1. A raised to 0 is basically 1. That means density is proportional to a constant, means it is not changing. It is independent of it. Next one. The force between two nuclear particles is F1, which are protons. And if both are neutrons, it is F2. And one is neutron and other is a proton, is basically F3. What is the correct relation between them? Hint is, consider electric as well as nuclear force. Consider electric as well as the nuclear force. Think about all the three scenarios. Okay, so we have both protons, then both are neutrons, and then one is a neutron and one is a proton. Okay, so both neutrons, and one is a neutron, one is a proton. Proton will definitely repel each other. Because of electric force. Neutron, no electric force. Neutron, proton, no electric force. But there will be nuclear force between them. So there will be a nuclear force to bind them. This neutron will also experience that nuclear force, guys. This will also experience nuclear force. Remember, nuclear force does not depend on the mass. It does not depend on the charge. Only depends on the spin. Let's assume the spins are same. And 1 femtometer means it's a short range thing. So nuclear forces are present. So I can see over here F2 and F3, basically both will be equal. This both will be equal. But if you check F1 over here, I feel because of the repulsion, the net force has been reduced. So F1 will, I feel, will be little bit less. F1 be slightly less. F1 will be slightly less. Make sense, everyone? So check it out. Yeah, F1 is less, F2 and F3 are equal. In second and third case, charges will not matter, okay, for the nuclear force, and there is no electric force. So the only force present is nuclear. So hence it should be equal. Doesn't matter whether it is a proton or a neutron. Here, protons will repel, nuclear force will try to bind them together. So that is the reason why you are seeing the net force has been reduced by some amount. Yeah, very good. That is the correct answer. C for captain. Moving on to the next question, guys, coming up on your screen. Let's see if we can do this. The radius of this nucleus is estimated to be this much. The radius of this nucleus is approximately how much? Okay, simple logic for this. See, radius is directly proportional to a raised to 1 by 3. So the radius of TE by radius of AL will be atomic mass number of T, which is 125 raised to 1 by 3, upon atomic mass number of AL, which is 27 raised to 1 by 3. So the next step, radius of T, which I don't know, radius of AL is 3.6. 125's cube root is 5. 27's cube root is basically 3. 3 goes with 3.6 1.2 times. So radius of TE will be 5 into 1.2, which is basically 6. Option A. Yes, option A is correct. Option A is correct. Yeah, 12's 5's are 60, so it will be 6 femtometer. Everybody? So I've just used this simple relationship. Radius is proportional to A raised to 1 by 3. Very good. Very good. Keep it up. Moving on to the next one on your screen. Now, there is binding energy based question per nucleon. For the parent is E1, daughter is E2. So who do you think is more or equal? Maybe this is the parent, this is the daughter, okay, and some other particles might be released or whatever. So for the parent, it is E1. For the daughter, it is E2. If this reaction is happening, that means it is becoming more and more stable. It is becoming more and more stable, and this is more unstable. That is why the parent split into the daughter. If it is stable, that means E2 will be less and E1 will be more. E1 will be more. So hence, what is the answer? E2 for the daughter nucleus is E2, binding energy. I think oh, sorry, I did it exactly opposite. My bad, guys. It is more stable, so more energy. My bad. So energy 2 will be more and energy 1 will be less. The more the stable it is, the more binding energy per nucleon. Correct? So if it is more stable, it has released a lot of energy. So this has more energy released. So Y has more energy released as compared to X. So E2 is more and E1 is less. So C for Captain Shreyas should be the correct answer. Correct. Very good. Why can't we directly do cube root of 125? We can. We have done the direct cube root of 125. Where did we not do? 125's cube root, I directly did it as 5 only. Yeah. We have just directly done it. Yeah. Cool. Even 27's cube root, I have directly done it as 3. Nothing. No extra step is there involved. Okay. Moving to the next one. M0 is the mass of oxygen. MP and Mn are the masses of proton and neutron. The nuclear binding energy of the isotope is. Observe carefully. It's oxygen 17.8. That means there were 8 protons and how many neutrons to give you the oxygen 17.8? Come on, quickly think and tell me. I want the answer in the chat box. We took the ratio, Sanvi says. Yeah, we took the ratio because I didn't need the constant. Because one thing's radius was given, other thing's radius was asked. That is the reason why we took the ratio. I know what is your doubt. You might be thinking, sir, we could have just done this question directly like this. No, sir, we could have just done this. R is equal to 1.2 Fermi into, what is it? 125's cube root. That is your doubt. Why did we have to use this? Very good question. Okay, never do this. Never do this, especially when other data is given. Maybe this constant's exact value is not 1.2. Maybe it is something else. Coincidentally, in this problem, it comes out to be 1.2. But what if they intend to keep the constant only something else? Then you will be in a soup, you will be in a trouble. So never ever do that. Okay, when especially two things are given to you, then always go by the ratio method. I know over here also you will get the same answer, 1.2 into 5, which is 6. This is also correct. But here they have assumed that I do not know the constant. So they want you to do it that way. Got it? Is this clear? This is some common mistake, common misunderstanding which many students have. And glad you asked it. I'm very happy you asked it. Okay. So now that we have to go to the question over here. Yeah, how many neutrons, guys? 9 neutrons. Can you see that? 17 minus 8. Yes, of course. 9 neutrons are there. So what is the mass defect going to be? The mass defect is going to be 8 times mass of the proton plus 9 times mass of the neutron minus the mass of the oxygen. Mass of the oxygen is MO. Mass of the oxygen is MO. That's it. This is the mass defect. Now whatever I get over here, if I multiply it with 931 mega electron volt, then I'll get it in mega electron volt, but I think C is mentioned over here. So if this is in kgs, I multiply by C square. If I multiply by C square, what I get is the energy. I will basically get the binding energy over here. So mc square. This is the mass defect into C square. So where is such an option over here, my dear warriors? It is basically this one. Okay. I think they had to put mod over here. Yeah. This was mod because this mass is less, this mass is more. Okay, this mass is more, this mass is less. So this will come out to be negative value. So this had to be a modulus value. Okay. Yeah, Krishna, I had to upload it. I will upload it, my dear student. Yeah, please. Yeah, I'll upload it. I know I was not able to do it because of JEE paper discussion, but I will definitely do it. The binding energy per nucleon of deuterium and helium is 1.1 and 7. If two deuterium nuclei react to form a single helium nucleus, then the energy released is how much? Interesting question. See, let's solve this. Binding energy per nucleon of deuterium is basically 1.1. So how do you make deuteron? Think about it. How do you make deuteron? You will take one neutron and one proton, and that will give you deuteron, 2H1, one proton, one neutron. If you talk about helium, basically you will need 2 neutrons and 2 protons. That will give you the helium nucleus. Interesting. Now, if I multiply this first equation with 2, I'll get 2 such nucleus of hydrogen. Interesting. And in this process, how much energy will be released? Let's calculate that. Let's basically calculate that from here. 1.1 mega electron volt per nucleon. There are 2 nuclear particles. So 2 into 1.1. But I also multiplied by this 2. So because of this 2, why did I do that? Because I can see 2n here, 2p here. To get similarity, I have multiplied it by 2. If I do that, I'll get 2 into 1.1. 1.1 mega electron was per nuclear particle, 2 particles, so into 2. And I have multiplied the equation with 2 so that they look similar, so that these two equations look similar. In case of helium, the electron volt which is released per nuclear particle is 7. There are 4 such nuclear particles. So 4 into 7 mega electron volt is basically being released. So from here to here, this much is released. From here to here, this much is released. So 7 fours are basically how much, guys? That is going to be 28. That is going to be 28, right? So 1.1 into 4, that's going to be 4.4. That's basically going to be 4.4 mega electron volts. So from here to here, 4.4. From here to here, 28. From here to here, how much do you think will be released? If I go from here to here. If I go from here to here, how much do you think will be released? Come on, guys, it's very, very straightforward. If I just go from here to here, just the difference of the two. So 28 minus 4.4. Is that making sense? 28 minus 4.4. What is the answer? 23.6. Yes, that is it. It is nothing but 23.6. As simple as that. If you just make a simple map of what is happening for hydrogen and helium and then realize, oh, in helium there were 2 neutrons, 2 protons. Why not multiply by 2? So I multiply by 2 here. And then I calculate how much energy was released by forming hydrogen, how much energy was released by forming helium. So if I go from hydrogen to helium, how much will be released? The subtraction of these two. That's all. As simple as that. Did you understand the logic? It's very, very simple and tricky, both. Okay, so these kind of questions are also again common. Okay, great. Moving on to the next one, and yes, we have reached semiconductors. Ready for the last part of this block 1? Ready for the last part of this block 1? Yeah, let's do this. Okay, now in semiconductors, what and all you should know. See, main thing is understanding band energy, understanding types of semiconductors, and then understanding diodes and their basic applications. That is the main thing about semiconductors. Okay, so let's start with band energy and those concepts. Then we'll go to types of semiconductors. Then we will go to diodes and their application and their characteristics. Okay, so let's start with band energy. Now, usually what happens is when you talk about an atom, the energy levels are lines. The energy levels are basically, these are the energy level lines for the electrons in different orbits. For the electrons in different orbits. But these are for individual isolated atoms. These are for isolated atoms which are very far from each other. Inside a solid structure, the atoms' energy levels are slightly different. They are no longer lines, but it is a band, it's a range of energies. Like you had K shell, L shell, M shell, N shell, which were lines of energies. Here you will have bands of energies. One band of energy, another band of energy, another band of energy, like that. So these are no longer energy lines. So these are nothing but energy bands. These are nothing but energy bands. And the gap between these energy bands is also called as the band gap. This is also called as the band gap. Is this absolutely clear? Everybody with me? Very good. Now, just like in an atom, some electrons will fill up some orbits will be vacant. Same way, the energy bands also can be filled completely, partially filled, or nothing filled at all. So maybe some band is completely filled with electrons. Maybe some band is partially filled with electrons. Some band is completely vacant, it's idle. There are no electrons in that particular band. So all the possibilities are there. Okay, keep these things in mind. Now, if you take energy bands like this, okay, this is partially filled, this is not at all filled, there are more bands above this, like this, there are more bands above this, like this. These are completely filled bands. The last completely filled band, is called as the valence band. This is called as the valence band, singular. But all the bands below that, everything below it is called as valence bands, plural, valence bands. When I use singular, it is the uppermost band which is completely full of electrons. Similarly, all the bands above this are called as conduction bands, plural. But when you use singular, it is the first band above the valence band, which is completely empty or half empty or half filled. So that is singular, valence band. Keep this in mind, valence band. Sorry, why did I say valence band? My bad. Conduction band. This is called as conduction band. Now, why is this called conduction band? Why is this called valence band? Here the valency is complete, that means it is full, it is happy. Yeah, the valency of the orbit or the band is complete. Here it is not complete. It would be happy to give away the electrons which are there and rather be empty, or acquire the electrons and be completely full. Here there is nothing over here, so it has no problem. Remember, being partially filled is always not what an atom wants. So that is why these electrons are always readily available. If by chance also some electron goes here, over here, they are not going to fill the band, so they can be easily expelled. They are not needed. So they are available for conduction of electricity. That is why these bands are called as conduction bands. Is that clear? Now, what happens is, the exact energy difference between a valence band and a conduction band, this difference is called as your band gap energy. This band gap energy plays a crucial role in deciding how the behavior of the solid will be electrically, whether it is a conductor, insulator or semiconductor. Just imagine you heat up, or basically you are at the normal temperature. At normal temperature, atoms will vibrate, they will collide with each other, and these electrons will jump onto the higher bands. All these diagrams which are shown, all this are at 0 Kelvin. That is the lowest temperature possible. That is the lowest temperature which is possible. But the moment you go at room temperature, it is quite possible that even if the band is empty over here, this is your conduction band, this is your valence band. So at room temperature, due to thermal collisions, what could happen? Some of the electrons might jump over here, so they are available for conduction. This can happen at room temperature due to thermal collisions. Keep this in mind. Some electrons might jump. But it is quite possible that even at room temperature, the collision energy is not sufficient to make the jump, because the gap is only so huge, you will not be able to jump. That is why some electrons, no matter what the temperature is, will never be able to reach the conduction band. And because it does not reach the conduction band, you will see it will not conduct, hence it remains an insulator. Hence it remains an insulator. So there are three kinds of categories that you usually get. One where your conduction band is really far from your valence band, and the band gap is much larger than a few electron volts, much larger than a few electron volts. So this kind of a device is therefore called as an insulator. It is therefore called as an insulator. Okay, this is an insulator. It does not conduct electricity. It's very difficult for the electrons to jump from here to here, even using the thermal energy. Then there are some where the valence band and the conduction band might actually overlap with each other. So there is no band gap as such. Very easily the electrons can make that jump. Very easily they can go here because they are overlapping. And because they are overlapping and the electrons can just magically go over there, that is why they are readily available to conduct. That's why they are called as conductors. That's why they are called as conductors. In some of them, some of the materials, it so happens that the conduction band and the valence band are not very far, but decently close enough. They are in the order of few electron volts. So the electrons can jump at room temperature. Those devices, those elements are then called as semiconductors. They are called as semiconductors. Is that clear? What is the difference between semiconductor, insulator and basic conductors? Everybody with me on this? Very good. Harish, yeah, you will have to solve more problems. Don't just solve the problems which I am doing here. Solve more problems, practice more questions. That's all. So use the crash course which is there for 999 rupees. There are exercises. You will hardly take maximum 1.5 hours, 2 hours to complete modern physics problems. Okay, just do as many questions as you can in exercise 1. Great. Now, the another special property of a semiconductor is that first of all, the band gap is of typical few electron volts. Second important point, in case of conductors, when you increase the temperature, what happens? The resistance also increases. Why? Because when you increase the temperature, more collisions happen and very difficult for the electron to find its way, because already there are so many free electrons. So in that, you increase the energy, these electrons also will make a crowd which are acting like mad fellows. So very difficult for these highly energetic electrons to find their way. That is why the resistance increases. But in semiconductor, that's not the case. When you increase the temperature, more electrons will go into the conduction band. There are very few electrons in the conduction band, remember that. So those few electrons will add up and it will increase the conductivity. That is the reason why you will see as temperature increases, resistance decreases. And you will see that the value of alpha is going to be negative coefficient of thermal resistance. Another thing is regarding Ohm's law. For conductors, voltage is directly proportional to the current, but you will see for semiconductors it is not so. In fact, voltage is not proportional to current. Not proportional, is not proportional to the current. In fact, if it is not proportional, that means the resistance, which is voltage by current, is also not a constant. Is also not a constant. So the resistance changes with the voltage. It's not like constant. You take a resistor, no matter what the voltage is, 5 ohms will remain 5 ohms, will remain 5 ohms no matter what you do. But for semiconductors, it will not be a constant. Keep this in mind. Okay? Very, very important distinguishing factors for semiconductor as compared to a conductor. For a conductor, the band gap is not even there. As temperature increases, resistance will also increase. Voltage is proportional to the current. Resistance is constant. That was for conductors. For semiconductors, I have written it down. Is that okay? Yep. Give me a thumbs up. Now, imagine what are the basic examples of a semiconductor. Let me also put it up. Germanium, silicon. All right, even GaS is also going to act like a semiconductor device. So all these are examples of semiconductor elements. Their band energies look something like this. Their band energies look something like this. Now, in case of a semiconductor like silicon or germanium, they have a valency of 4, just like carbon, and they can form long chains just like carbon makes with other carbon atoms. That is the basis of organic chemistry, right? Same way, imagine you take silicon, 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 like that. It can make huge chains like this of bonds between them. You'll start forming bonds between them. Each line represents a bond, that's all, between these silicon atoms. And you will get a big chain of silicon atoms in that solid. But like I said, the atoms are always in a state of random motion. So maybe this silicon will go here, will go here, will go here. Sometimes the bonds can break. Sometimes these bonds do break. And what you will see is, if during the random motion, let's say this particular silicon just happens to reach here, you will see that one of the bonds might get stretched, one of the bonds might just get stretched, and it might just happen to break. It might just happen to break, correct? It might just break. And in this scenario, when the bond breaks, what will happen? What will happen? You will see that maybe the electron is retained by somebody. The electron is retained by somebody. So let's say the electron is retained over here, and there is a deficiency of electron at the other place. There is a deficiency of electron at the other place. So the deficiency is called as a hole, and an electron is also being created. Electron is also being created. So you get a electron hole pair. You get an electron hole pair. That's what you will get. Electron hole pair is what you get due to thermal energy. And this happens throughout that solid. It happens throughout that solid. Remember that. So in that big solid that you have of silicon everywhere, you will probably see an electron being formed here, electron being formed here, and simultaneous hole being formed here. And what will happen is, maybe this electron might go here like this and satisfy this hole. This electron might go somewhere here and fall into this hole. This electron might go here. This electron might go here and fall into some other hole. Some electron from there will fall here. So when this happens, electrons are also moving, and when this electron goes here, this hole will be complete. This hole is here. So, it's like saying, when this particular electron left this hole and filled this particular hole, you will see that in the next instant there is this particular electron in this hole. So that job is done. A new hole has been created here. So the hole has shifted from here to here. The hole has shifted from here to here. The hole has been shifted from here to here. Earlier both of them were together. Earlier you can think as if both of them were together. There was nothing. The electron hole pair was created. This electron went and fell into this hole. So now this hole has gone here. So there is motion of hole. So I can say there is basically motion of holes, and also there is motion of electrons. You can see electrons are going like this, holes are going like this, holes are going the other way. And this process is continuous. Electrons are going here, holes are going here, holes are going here, electrons are going here, every possible direction. And as a whole, you will see that the total current due to electrons will be 0, and the total current due to the holes will also be 0, because it is not connected only to anything. It is not connected only to anything due to basically random motion. Keep this in mind. Now what happens is, imagine somebody takes this silicon semiconductor solid and they happen to connect it to some battery. Battery. What you will see is there will be a voltage difference created, and immediately, because this is positive and this is negative, you will probably see more electrons going here, few electrons going here, more number of electrons will be going here. And probably you will see more holes going like this or shifting their positions like this. Very few holes will be going in this direction. Hence, because electrons are going this way, it's a negative charge. So it's as good as saying the current due to electrons is in this particular direction. Because negative charges are going this way. Current is the flow of positive charge. Same way, holes is like deficiency of electron, means like positive charge. So if holes are going this way, it's like saying the current due to the hole is in this particular direction. So both these currents are helping each other. That is why, my dear students, you will see that there will be a total current, which will be formed, which is the current due to the electrons and the current due to the holes. This is very different from conductors. In conductors, there is no electron hole formation and all those things. Only in semiconductors you will see this, and that is the reason why we say the current in a semiconductor is due to holes also and due to electrons also. So the current is due to, current in a semiconductor is due to electrons and holes. Both. Keep this in mind. Everybody fine till this point? So I have explained you how the current flows in a semiconductor and how bond formation and breaking happens due to thermal energy, and how the net current is 0 usually unless you connect a battery voltage. Now imagine I take a semiconductor and I tell you I can classify it into multiple different ways. A semiconductor can be classified into multiple different ways. The first one is called intrinsic semiconductor. The second one is called extrinsic semiconductor. Intrinsic means basically pure semiconductor. It's very pure there is no adulteration. Like maybe some people add some colors, some ingredients in the food. That is adulteration. That is doping. That is not pure. If in gold you add copper, that is adulterating it. You are doping it. So pure is basically intrinsic. Like only silicon, 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 silicon everywhere. That is intrinsic semiconductor. It is not doped. Extrinsic means it has been doped. It has been added with some additives. And there are two kinds of additives that you can add. There are two kinds of additives that you can add. One is P-type. One will make it P-type of semiconductor, where you add a trivalent impurity. Whereas in N-type, the second type, you add basically a pentavalent impurity. In case of intrinsic semiconductors, what happens is the number of electrons is equal to the number of holes which are present, and the electron holes are equal in amount because equal pairs are formed, equal electrons, equal holes. That concentration is called Ni. Number of charges per unit volume, holes per unit volume, electrons per unit volume. That is called intrinsic semiconductor concentration. This is just called as intrinsic concentration. Intrinsic semiconductor charge concentration, you can say. Intrinsic charge concentration. But in case of P-type, P stands for positive, means holes are more. Exactly. So you will see the number of holes is much larger than the number of electrons which are there per unit volume. In case of N-type, it's the other way around. The number of electrons are more than the number of holes which are there per unit volume. That will make it N-type of semiconductor. Is this chart clear? The different types of semiconductor? So any semiconductor can be classified as intrinsic semiconductor, external, extrinsic. That means you have added something. In intrinsic, the number of electrons and holes are same. Just like over here. The bond breaks, electrons and holes are formed together, so they are same. So it is called as Ni. But in extrinsic, you will see holes are more or electrons are more, and that is why you will see that it will be called as either P-type or N-type depending on which quantity is more. But one thing is there, whether it is P or N-type, if you happen to multiply in any one of them, NH multiplied by Ne, you will always get the intrinsic semi-concentration square. Intrinsic charge concentration square. So that is what you will always get. Very, very important for extrinsic semiconductor. Keep this in mind. Okay? Clear till this point? Let me add some more things to P and N type on the next page. When we talk about P type of semiconductor, that means trivalent impurity, means something like, imagine usually silicon, etc. would have bonded with each other, but just imagine you added a trivalent impurity, like imagine aluminum. It can't make 4 bonds. It has 3 valency, so it can't make 4 bonds. It will only make 3 bonds. So the silicon which is over here, which would otherwise had made bond with another silicon atom, that is unable to make that bond. It is unable to make that bond. So because of which you will see that there is a hole which is created in excess. There is a hole, deficiency of an electron is there. Deficiency of an electron is there. So an additional hole is basically created. Additional hole is basically created, which improves the conductivity. What does it do? It improves the conductivity. In fact, remember the semiconductor energy band graph which I had drawn some time back. This was the completely full band, that is called the valence band. This was the conduction band. The moment you add aluminum, what happens is it creates a new conduction band over here of vacancy because of P type of semiconductor. So earlier this electron had to jump here, but now the same electron has to only jump here, which makes it easier for the jump, and that's why it is easier to conduct. Easier to conduct. It becomes easier to conduct by adding that doping material, that impurity. Yes, very good. Similarly, for N type of semiconductor, what happens is, similarly for N type of semiconductor, what happens is, you put a pentavalent impurity in between. You put a pentavalent impurity in between. Something like this. Like phosphorus, example. So the valence is 5. So phosphorus has an extra electron. Which again increases the conductivity of the material. So if you look at the energy band diagram, things will be very clear. This was your valence band. This was your normal conduction band. It creates an additional valence band over here because of that N type. So earlier the electron from here had to jump till here. Now it gives an additional source of electrons which only has to jump over here. So it becomes easier to conduct. It becomes easier to conduct. Keep this in mind. Everybody clear till this point? Yes, very good. Keep it up. Keep it up. So I have explained you what is p-type, how the band looks like, what do you add, what does it create, and the flowchart and the relationship. Now, there is one more thing. Whether you take p-type, n-type, any type of semiconductor does not matter. Since the total current is the current due to electrons and current due to holes, we can also associate the conductivity of the semiconductor with drift speed and all those other things. So, what is that formula? In general, remember conductivity, which is nothing but 1 by resistivity sigma was nothing but number of charge carriers into the charge into mobility. This was charge, N is charge per unit volume. This is the charge itself, and this was mobility. Remember mobility in current electricity, it was the drift speed per unit electric field. This is nothing but the charge itself. This is the conductivity of any conductor. Charge per unit volume into charge into mobility. But for a semiconductor, I need to modify it slightly differently. For a semiconductor, I need to modify it slightly differently because there are two types of charge carriers. One is holes, one is electrons. So it is sigma due to electrons, which will be nothing but number of electrons per unit volume into the charge of the electrons into mobility of the electrons. and I have to add to it the conductivity of the holes. Conductivity of the holes, just like I put it over here. Current of holes plus current of electrons, same way conductivity of electrons plus conductivity of holes. So conductivity of holes will be number of holes into the charge of the hole, which is again E only, and mobility of the holes. So that becomes the conductivity of a semiconductor. Very, very important formula. Very, very important formula. It comes from this. It basically comes from this. Is that okay? Clear? And usually it so happens that the mobility of the holes is much, much lesser than the mobility of the electrons. Why? Because they are very easy to move. Electrons are easy to move. Very easily they can move. Mobility of holes is less because it's very difficult for them to shift. Electrons can easily move from one place to the another. They will move at the high speeds. But holes depends on which electron will fill them up. So holes mobility is little bit more difficult as compared to electrons. That's why usually this value is less, and usually this term just vanishes because of this guy being very, very less. Keep this in mind. This guy being very, very less. Okay, keep this in mind. Okay, so I have told you about all the formulas. Even you can block this particular part. Okay, great. Now that we have understood what is P and what is N, shall we go to P-N junction? Shall we go to P-N junction, guys? Yes. Okay, very good. So let's understand what is a P and N junction. Basically, now you have two different conducting properties. One is due to excess holes, one is due to excess electrons. Each creates their own new conductivity, but in different manner. So what happens when I bring them together? That is called as a P-N junction. P and N junction. So let's see what exactly happens. So what am I exactly doing? There is silicon, like this, silicon, silicon. Imagine on one side, I put basically phosphorus, that is pentavalent, and on one side I put aluminum like this. So this will become P-type semiconductor, and obviously this side will become N-type of semiconductor, and there is a junction in between. These two are joined together, that's why it's a junction. Now when I have usually asked people, is P-type positive, N-type negative? Students say, yes sir, P is positive, N is negative. But that is not correct. I'll tell you why also over here. If I go back, many people say, sir, aluminum, if I put P-type, so hole is created, so it is positively charged. Nothing like that. Yes, one electron is less, but don't you forget, aluminum has a different nucleus only. So there is one proton less as compared to silicon. So electron is also less, proton is also less, so they both nullify. So never ever say P is positive. That is wrong. That is the notion that many students have. Many students also think, sir, phosphorus gave an extra electron, so this is a negatively charged solid. That is also wrong. Don't you forget, phosphorus has a different nucleus than silicon. So there is one extra proton also inside the nucleus. So that extra proton and this electron will cancel out, nullify. So there is no excess charge. Understand that. Do you get it, my dear warriors? So understand this, that over here, a lot of people think about this. Caution. P and N type are neutral in charge. They are basically neutral in charge. Is that right? Everybody with me? Yes, very good. Now, Here also this is neutral, this is neutral. But let's understand what do they want. Aluminium means there are holes which are there. There are extra holes which are there. Phosphorus means there are extra electrons which are there. Apart from that also, electron hole pairs are being formed. Maybe they will also form a hole and an electron pair. Maybe they will also form a hole and an electron pair. Hole electron pair. Hole electron pair. But you can see extra holes are there. Here extra electrons are there. Obviously, what is the need of the hour? What is the need of the hour? Guys, obviously these electrons will tend to fill up the holes. You will definitely see these electrons going over here. You'll probably see maybe this electron goes over here, maybe this electron goes here, like this. Maybe this goes like this over here. Okay, sorry, hole will not go, electron will go. Something like this. So you can clearly see, you can clearly see how the electrons are moving. You can clearly see how the electrons are moving. So the electrons and the holes, they diffuse into each other. This process is called as diffusion. This is called as diffusion when unequal concentrations are present. One side has helium, one side has oxygen. Oxygen and helium will mix. Oxygen will go here, helium will go here to distribute and even the concentration. So one side had more N, one side had more P. So they will diffuse into each other to make the concentrations equal, right? Everybody with me? So in the next step, here is what I would say. This is our semiconductor. This was our P type. Okay. This was N type. This was our P type semiconductor. So what will happen is, because more electrons are going like this and the holes will go like this, in this particular process there will be a current which will be formed. Electrons going here is same as positive charges going there. Holes going there is same as positiveness going there. So you will see that there will be a drift current which is being formed. There is, sorry, not drift, diffusion current which is formed. Diffusion current, currents will diffuse like this in this particular direction. Diffusion current will be formed because of the diffusion process. Because of the diffusion process. Hence, what you will see is P will actually become positively charged, sorry, my bad, negatively charged, and N will become positively charged. This will become negatively charged and this will become positively charged. So there is a voltage difference which will be created. There will be a potential difference which will be created between them. This is positively charged, this is negatively charged. Obviously negative means there will be low voltage over here. Positive means there will be high voltage over here. So if at all I draw a graph, this is distance, this is voltage, origin is the junction. You will see the N side will be at higher voltage, the N side will be at higher voltage, the P side will be, the N side will be at higher voltage like this, and the P side will be at a lower voltage like this, will be at a lower voltage like this. So you can see clearly there is a voltage difference. There is a voltage difference. This is called as a potential barrier. This is called as a potential barrier. The voltage difference between N side and P side, that is called as a potential barrier. Is this point clear till everyone? Yeah? Okay. Now, because this is high voltage, this is low voltage, remember electric field. How does electric field go? How does electric field go? High voltage to low voltage. So you will notice that there will be electric field in this direction. Electric field will be in this direction. And this region from here to here, this region from here to here, if you measure this particular distance, this is also called as the depletion zone. Depletion zone, let's say I call it as X. Then the electric field E is dV by dr. So E will be nothing but V divided by the depletion zone, which is basically X. This formula you know it from electrostatics. This formula you know it from electrostatics. E is equal to dV by dr. Okay, E is nothing but your dV by dr, magnitude wise. So voltage is V, distance is Z, X, whatever. So E is dV by dr, we have used that. That is the field which is created in this depletion zone. So what happens next after this? Okay, let's have a look. Let's have a look. P and N, okay. So this was P, this was N. Remember, there was an electric field like this. There was an electric field like this. This was the direction of the electric field. Remember, there was diffusion current like this. Diffusion current like this. Everyone? Now what happens is, because of this electric field, if by chance there is a whole electron pair which is formed, immediately think that the electric field will apply an electric force onto the holes and the electrons. Electric field will apply an electric force on the electrons and the holes. How? On the holes, the force will be in the same direction as the field, whereas on the electrons, the force will be in the opposite direction. The force will be in the opposite direction. So negative charge is going here, positive charge is going here. So effectively positive charge is going towards your left side, correct? Positive is going here, negative is going here, means like positive is going here only. So total charge positiveness is going towards the left side. So you will see this process will cause the motion of electrons and holes in this depletion zone, in this particular depletion zone, and this can only happen when electron and hole pairs are formed and the electric field forces the electrons and holes here and there. So there is a new current which is created in the exact opposite direction. This is called as the drift current. What is this called? The drift current. I hope this is clear. Yeah, I know, Shishant, you are waiting on the J channel. Hold on. Usually, what happens when you do not connect anything? When you do not connect anything means it is unbiased. For unbiased condition, what will happen? The diffusion current will be equal to the drift current. Is that clear? Everybody with me? Both of them are going to be equal. So what will be the total current? Put it up in the chat box. It will be a big fat 0. But if somebody decides to do something like this, say for example, this is P type, this is N type, and they decide, listen, I am going to connect the P type to positive and the N type to negative. Then what happens is, the drift current does not reduce, drift current stays as it is. It's the diffusion current which increases. This kind of biasing, this kind of conditioning is called as a forward bias. And in such a forward bias, you will see that the total current is nothing but the diffusion current minus the drift current. Usually this is very, very small. This is the major contributor. And what happens in forward bias is, till a point the current does not increase significantly, because remember there is a barrier which is there. I showed it to you here. So this barrier reduces, and once the barrier is destroyed, there is a sudden surge of the current. So, oops, sorry. That's what you will see. So this current increases after the barrier is broken. So this current increases suddenly after the potential barrier is broken, is basically broken. This is called as your forward bias. The exact opposite happens when you take, this is your P type, this is your N type. You connect the P to the negative and N to the positive. Now, the current should go like this. In this case, the diffusion current reduces, but the drift current does not change much. The drift current is still the same. Is the diffusion current which basically reduces. This is anyways going to be small. So you are seeing that there is a net current which is created. So there is a net current which is created, which is the drift current in this case, which is larger, minus the diffusion current. Remember, drift current is always very small. Diffusion is even smaller now. It is even smaller now. So this current which you get is so small, you often call it as the leakage current. You call it as a leakage current because it is very, very, very small. This kind of conditioning is called as reverse bias. This is called as your reverse biasing. So in reverse bias, there is hardly any current, whereas in forward bias, there is a good amount of current which flows in. There is a good amount of current which is going to flow in. Is that right? Hence, you will see that if you take a P and N type of material, if you pass the current from here, it will flow very nicely. But if you pass the current like this, it will not allow so much of current. Correct? It will not allow so much of current to pass in the other direction. So it allows in one direction, does not allow in other direction. It's like one-way traffic. So such things are basically called as a diode. So a PN junction acts like a one-way traffic road, for current, and such devices which allow current in one direction only, they are called as a diode. Hence, the symbol of a PN junction is often like this. So this side is P type, this side is N type. This arrow mark shows the direction in which it allows the current. You can see it is allowing the current in this direction. It blocks the current in the other direction. Is that clear why PN junction is called as a diode? So now if you take current versus voltage graph, remember I was telling you current is not proportional to the voltage. That's exactly what you will see. In this side, voltages are positive. That means this side is nothing but forward bias. This side voltages are negative, so this is reverse bias. So when you increase the voltage, you will see the current will increase, but after a point, you will see there is a sudden increase. Of the current. So this point is often also called as the knee voltage. Where the current suddenly increases. Usually, the knee voltage for silicon is 0.7 and for germanium is 0.3. How do I remember it? S for 7. When you write 7 in words, S-E-V-E-N, S, 7. And 0.7 plus 0.3 is 1. So that's how I know germanium is 0.3. Okay, that's how I remember these values. In the reverse bias, it is leakage. So hardly any current is there, you can see. So there is very less current. It is leakage current. But after a point, when you apply too much reverse bias voltage, a breakdown occurs. So this is called as the breakdown, reverse bias breakdown, where the voltage roughly remains constant. It does not change no matter what you do. You cannot increase the reverse voltage beyond this point. That is your reverse breakdown voltage. Reverse breakdown voltage. This is how the basic graph looks like. You should also know a couple of things over here. Like especially when we talk about current voltage graph, and let's say the graph is something like this. If by chance you take any particular value of current and voltage over here, resistance V is equal to IR. So R is equal to voltage by current. This is often called as just the resistance of the semiconductor. This is just called as the resistance of the semiconductor. You will clearly see that if I take I1 here, V1 here, and then if I take some another value, V2 and I2 over here, okay, I2 over here, these both won't be same. Like R1 won't be equal to R2 because your V1 by I1 won't be equal to V2 by I2. Reason is slope is not constant. The slope is not constant. So the resistance keeps changing, okay, with the voltages. It is not like conductors where it is always a constant. Here we have one more term called as delta V, and if I put this as delta I, we have a term called as dynamic resistance, which is instead of voltage by current, you put delta V by delta I. This is also in ohms only, but the way it has been defined is slightly different. It's how the voltage is changing with the changes in current. It is like delta V by delta R, that is called as the dynamic resistance. Some questions are there on that also. Dynamic resistance. Thank you, just an ordinary person. Thank you so much. Hello, Navya. Very good. Okay. So I hope till this point everybody has been following, guys. I hope, yeah, I'll be continuously talking now, and we'll try to complete as much as possible. Okay, so concentrate quickly. Okay, now this is done. Okay, this is done. Now that you understand what a diode is, what is the current voltage characteristics, etc., there are some applications of diodes, and I will tell you some of the applications of diodes. So let's go to the applications of diodes. The first one is LED, light emitting diode. LED, the symbol for that is just put two arrow marks coming out of it. Light emitting diode, which is used in screens of mobiles, even headlights these days come with LEDs, etc. Torch, LED torch, so many of these things, indicators. That is a typical application of it. An LED is always used in forward bias. Remember that. It is used in forward bias, obviously, or else no current will go, no light will come out of it. And the working principle of that is as simple as when you have a PN junction diode and you see there is some hole here and there is some electron here, and maybe the electron is going and jumping into this. So when the electron goes and fills up the hole, it's like an electron coming from higher energy to lower energy. So it's like energy of the electron is going from a higher state to a lower state. So there is a difference of energy. It is going to a low energy state from a high energy state. low energy state on the hole, and this is at the start. So in this process, because the electron jumps to a lower energy state, what should happen in this particular process? Obviously, a photon should be emitted. Obviously, a photon should be emitted. That is the reason why you will see light coming out of it. If that energy gap is delta E, then that will be equal to the energy of the photon which will come out of it, which is nothing but hc by lambda. So this is the formula for the wavelength of light which will come out if delta is given to you. If it is in the visible spectrum, you will be able to see it, else you will not be able to see it. Okay guys, everyone? Very nice. Awesome. Let's move on to the next one. Second one is called as a photodiode. It's exact opposite of this. The symbol for that looks somewhat this way, right? The examples of this is in sensors, and they are always used in reverse bias. Why they are used in reverse bias, I'll tell you in a very simple way. See, if you look at the current voltage graph, if you see forward bias, the current increases with voltage like this. When more light falls on the semiconductor, the current will increase slightly, maybe like this. If you increase more light, maybe the current might increase like this. It's changing, but it is not visible so much. But imagine this in the reverse bias diagram. In the reverse bias, let's say there is leakage current over here. Like this. When you increase the intensity of light, more light is falling onto it, more current will be formed. So maybe the current goes like this. You increase more light, more current will be formed, and it will go like this. It's like saying earlier the current was 10 amperes, now it became 10.01, then it became like this. Let me put it over here. 10 amperes, then it became 10.01 amperes, then it became 10.02 amperes. Hardly any changes are observed. But in this case, in the reverse bias, imagine the first time the current was 10 milliamperes, then it became 20 milliamperes, then it became 30 milliamperes. Don't you see the change is significant in reverse bias as compared to in the forward bias? Because the current is only so small, so a small change is more noticeable here. When the value is huge, a small change is not seen. But when the value is small, even that small change is seen. That is why you use it in the reverse bias. Is that clear? Everybody? Yes. Very nice. Very, very important. Okay, so that is a photodiode used in sensors. Light is falling, current increases. Automatically, the circuit gets activated. Like sometimes, you put your hand in between something, the circuit gets triggered and alarm rings. So there is a photodiode involved over there. Okay. Moving on to the next application. My dear students, you have basically the solar cell. Solar cell is nothing but it's just based on the photoelectric effect only. So you basically have light which is falling onto the PN junction. Here you take out wires. And let's say This is some load over here. There is some load over here. So this light, this incident light, what it does is basically it creates extra holes and electrons. Extra holes and electrons pairs, because of which you will see the conductivity increases. The conduction improves. And once the conduction improves, you will see more current will flow onto it. You will see more current will flow onto it. And once the current flows, what will happen? Once the current begins to flow like this, and let's say the load resistances are, you will get a voltage across the load. And this voltage is nothing but I into R. So you will get an output. You will get a voltage from that PN junction. You will get an output voltage from the PN junction. Is that understood? Clear, my dear students? This is how a solar cell works. You don't need a battery for this. See, for photodiode, you will need a battery. For LED also, you will need a battery. But for, solar cell, you don't need any battery. It is acting like a battery. It is going to give you voltage. Solar cells, we all have seen solar panels kept on the roofs. So it is exactly based on this principle. Light falls, more holes and electrons are created, conduction increases, current begins to flow, and you will see that, the current creates that voltage. Clear? Okay. Next type of diode, which you should know, which is basically Zener diode. Now this Zener diode is a special type of diode which has high doping material. Okay, high doping material, and it is also used only in the reverse bias. And the symbol for that diode is like the Egyptian dance. Have you seen Egyptian dance? They do like this. That is Egyptian dance. Okay, so that Egyptian dance. Don't make a meme. I think Pandu is not there, but Pandu, if it was there, might make this also as a meme. So 2 dance performances by Captain Shreyas. So this is Egyptian dance. That is basically, okay, your Zener diode. Okay, that is a symbol for it. As simple as that. Okay, so this is used in the reverse bias. So what is so special about reverse bias? Do you remember? If this was current, this was voltage. This was forward bias. In the reverse bias, remember, after a point, there is a breakdown which happens. This voltage is called as the breakdown voltage. This is called as the breakdown voltage, which is constant. So you cannot increase the voltage beyond a certain limit. No matter what you do. So just imagine this. This is our Egyptian dance. Always remember this, Pandu, yaar. Very simple. I will show this. Look at these moves. By Pandu. I'm pretty sure if there was a champa here. Oops, I should show it like this. Oh, wait. That is Champa loving Pandu because of his dance steps. And I think Champa will also dance after this. What is the dance moves? It's like this, so like this. Yes. Oh, yeah. Perfect. What a dance. Yeah. So imagine this Zener diode like this. And maybe its breakdown is 5 volts, who knows, and there is some resistor here, and there are 2 points. This is your input. And here you measure the output, and here across this you measure the output. So this is output and this is your input, and let's see how this table fills up like. So imagine I give different values of input, like say 5 volts, then 7 volts, then 10 volts, then 9 volts, okay, something like that, and maybe even 20 volts. Because the breakdown voltage is example 5 volts, always the output will be 5, 5, 5, 5. You are giving 20, but here only 5 volts is coming. So you will be wondering, sir, where is the rest of it going? The rest of it is going in basically this other resistance. This other resistance is there. The voltage across that resistor will be dependent on these two values. This is 5, this is 5, this will be 0. 0 plus 5 is 5. So this will be 0. 5 plus 2 is 7. 5 plus 5 is 10. 5 plus 4 is 9. 5 plus 15 is 20. So if you know this voltage, you can find this given this, or this is given, you can find this. This is given, you can find that. That is the logic behind solving Zener diode questions. Yes, all concepts covered. Got it? Everybody with me on this? Clearo? Perfect, perfect, perfect. Okay. Now that this particular application is clear, how Zener diode is used and why we use it in the reverse voltage, because the voltage becomes constant in the breakdown region. Let's go to the last application of the diode, and that is basically called as rectification. Rectification. What is rectification? It is a process of converting AC into DC. The example of that is your adapter, mobile adapter or charger, right? Your mobile adapter or charger, the adapter you plug in, that is AC. What your mobile works on is DC. Your electric scooter or car, AC into DC, battery stores in DC. So that process of converting alternating current into unidirectional current is called as rectification. Now there are two types of rectifications. So we'll see both those kinds. Number one is half wave rectification, and the second one is called as a full wave rectification. What is the difference between it? See, imagine this is your input, this is your output, input, this is your output graph. You are giving alternating current, means positive, negative, positive, negative. Alternating current, positive, negative, positive, negative. Correct? Half wave means exactly half the wave. So, other half is a complete waste. The output will be basically like this, nothing, like this, nothing, and this continues. In full wave, the entire wave gets rectified, means it will be like this. This will come on the top, this will come on the top, and this will continue like this. The entire wave gets utilized, so full. Here half of the wave gets utilized, that means half. Understand what is the meaning of it. Half wave means, see, current was positive, means let's say current was going like this. So the same current is going here, it is going in this direction. But now current has become negative, means current has reversed the direction. But you can see it is completely blocking it. You can see it is completely blocking it. Again, current is in this direction, it is allowing it. Current is in the other direction, it is blocking it. So current has been made to go in one single direction. So how do you build that circuit? It is simple. You take a AC source, and you just connect a simple diode to it, and let there be a resistor. That's enough. And all you do is measure the output over here. You measure the output over here. That's it. So you will see in the positive half cycle, when this is positive, this is negative, this diode will become forward bias. It will allow the current to flow. It will allow the current to flow. But the moment this becomes negative, this becomes positive, this diode will become reverse bias and the current in this will be 0. So the output will also be 0. So positive 0, positive 0. That's how a half wave rectifier works. That's how a half wave rectifier works. Is that clear, my dear students? Everybody with me? In case of a full wave rectifier, what they do is they generally use something called as the center tap transformer, which means it's like having two windings on the secondary. Remember, transformer, primary, secondary. So it's like having two secondary coils and two of their terminals are joined together. This is the center and you are tapping it. Tapping means together you are pressing it. So it's center tap transformer. This is often called as the center tap transformer. That's what they use. And then they have a diode here like this. And then they also have a diode here like this. And then they have resistor here like this. And what you do is you measure the output here. You measure the output across these 2 points. Across these 2 points. This is where you measure the output. So what happens is in the positive cycle, this is positive, this is negative, let's say this is 0. This is positive, this is negative, AC polarities keep changing. So this diode will become forward bias. This diode will basically become reverse bias. Because negative is connected to P. Here positive is connected to P. So that's why this is forward. So you will see that the current will go here, come like this and go through this resistor like this. In case of the negative cycle, this will become minus. This will become positive. Relatively this is 0. You take anything as 0 potential, this is lower, this is high. So positive connected to P, this will become forward bias and this will become reverse bias. Because this is forward, the current will come like this. It will continue its journey, go inside and come out from here. In either case, the current is going in the same direction. That is why this will use both the cycles and convert it into unidirectional current. That is why the output will be only on the positive side. Is that clear, everybody? So that is how a full wave rectifier works using a center tap. Center tap means two transformers connected together. Center, you have tapped it together. That is the center tap transformer. Now there is one small part in your NCERT which is given. So if the example output which is coming is not very good, it has these things. They are called as basically ripples. They are basically called as ripples. Ripples are there. Ripples means the DC current is not constant. It is basically not constant. So what is usually done is you take a capacitor like this, connect it over here and then you measure the output. Then you measure the output. Now the moment you connect a capacitor, so this is basically the current which was coming from the rectifier. It was not constant DC, it was fluctuating DC. Here the output that you get is very smooth like this. So it is almost a constant DC. And this happens because of the capacitor. So usually you use a capacitor for filtering. Basically this is the filtering process to basically smoothen out the curve. And why capacitor? Because capacitor will store the charge when required. When current is dropping, it will give that charge. When current is increasing beyond a certain limit, it will acquire that charge, store it, and when it goes down, it will give it. So it will not allow it to fall, not allow it to rise. As and when required, it will save and give it back. That is why it is able to smoothen that curve. Understood? Is that clear? Yes, Surya, the notes will be available on the Telegram channel later on. That is the reason why you use a capacitor. Okay. So let's solve some questions based on semiconductor quickly, guys. Okay. The increase in the width of the depletion region, remember that zone which is there, in a PN junction diode is due to both forward and reverse bias, increasing forward current, increasing forward bias, reverse bias only. Where do you think that depletion region which is there will increase? The depletion region, where do you think it will increase? Only in the reverse bias? Yep, only in the reverse bias, because in the forward bias, that barrier reduces, the zone, depletion zone reduces and vanish, and sudden surge of current is there. In reverse bias, in fact, you are going to make it worse. The depletion zone is going to become even more. The barrier is going to become even larger. So that is why only in the reverse bias. Correct. Moving to the next one. PN junction diode changes the temperature. Change in the temperature due to heating does not affects only forward resistance. What do you think about this? What do you think about this? Come on, my dear warriors. When you heat it, what will happen? The entire characteristics will change. Why only forward? Why only reverse? The entire characteristics will change. The overall resistance only will reduce. So the overall currents will improve, whether forward or reverse. Everything will be affected. Yes, everything will be affected. Very good. Awesome. Next, in forward biasing of the PN junction diode, which terminal is connected to which terminal, which becomes thick, the depletion becomes thick or thin? Come on, think about it. Welcome, Krishna, means a lot. What do you think, guys? Forward and reverse bias. D option? Sure. Very nice. Very good. The positive terminal is connected to the P side and the depletion region becomes thin. Correct. Forward biasing. Forward means P to positive, N to negative. And the depletion zone becomes thin, barrier becomes small, and there is a good flow of the current. Yes, that is why option D. Very good. Now, there are more questions which I'll be practicing, but let's go to logic gates question. Now, you'll be like, sir, you haven't taught logic gates. I'll tell you one simple thing. What you can do, the best thing to do for logic gates is just go to the channel and just search for logic gates Shreyas. Okay, logic gates Shreyas. Just 2-3 months back, I have conducted this class. Only watch this 1 hour 45-minute class, because logic gates involves little bit of here and there things, some tricks which I have nicely told in this particular lecture. So just check this particular lecture out. It's a very nice lecture. I'm pretty sure you're going to enjoy this. A lot of students have enjoyed this lecture. So check this lecture out. I have taught logic gates in detail. So I feel you will enjoy this class, and then come back to these questions which I am going to discuss. That will be better. Is that okay? I also have to go to another channel because JEE discussion is happening, but I'll show you some questions which are there over here. If you have attended that class, it will be fine. Will you be able to attend that particular lecture, guys? Check. Give me a thumbs up. Check the previous session. Check the previous session on the channel. It's a beautiful class. Okay, so it's a simple thing which you can do. Okay, right. Okay, so let's just do some questions maybe on this logic gates. The output of the logic circuit shown over here. In that lecture, I have told that whenever you see such a diagram, remember to convert it into a NOT gate. This is nothing but a NOT gate, and this is also a NOT gate, and there is a saying that two wrongs make it correct. Two wrongs make it right, right? So two knots will just be nothing. So you will just have, what is this? This particular logic gate and just a wire over here. And what is this? This is basically a OR gate, if I'm not wrong. So hence the answer will be OR gate. Directly you can mark it up. Okay, so this questions are very, very simple. I'm pretty sure you will enjoy it also. Which of the following gate is also called universal gate? This is also something which I have told in that lecture. It is nothing but your NAND gate. So NAND and NOR, using NAND and NOR, okay, you can make any gate that you want. Okay, that's why they are called universal gate. Any other gate can be made using NAND and OR. Okay, don't get confused between that and over there. What about this? The correct Boolean operation represented by the circuit diagram shown over here. What do you think it is representing, guys? Is it NOR and OR NAND? Remember, high means 1, high voltage, true, low means false, right? So think logically, this is high voltage, this is ground. So if both are at 0, then what will happen to the bulb? What will happen to the bulb? Just think about it. What will happen to the bulb? Both are off, so the entire current will flow through the bulb. That means the bulb will have current. It will definitely glow, right? It will definitely glow. So it will glow. Let's say I close this. Where will the current go? Nothing. It is stuck over here. So even if this is 1 and this is 0, or this is 0, this is 1, even if I close this and this is open, current can't flow in this branch. Even if I close this and open this, current can't flow in this branch. Doesn't matter, this branch is completely useless. The high voltage to low voltage current will flow and the bulb will obviously glow. So hence in this case also the bulb will glow. If this is 1, this is 1, both you are closing. So now the current has an alternate way of going like this. So no current will pass here. So the bulb will basically not glow. The bulb will basically not glow. So this kind of operation is nothing but a NAND operation, guys. When both are true, the output is false. That is a NAND operation. Yes, definitely. That is a NAND gate. Very good. Very good. Very good. So yes. All right. We have come to the end of the class, and this is a quick reminder for all of you that, you know, the NEET crash course, your last ditch effort. If you think that everything else has failed, and if you feel that, sir, I am at 500, I want to go to 550, 580, 600. Sir, I'm at 600, I want to go to 650. Sir, I'm at 400, can I get to at least 550? Sir, I'm at 300, I want to come to 450. In the last 4 weeks, this is your last try. Trust me on this. And the batch has just started, and my lecture is tomorrow with other teachers who are there in this batch. I'll be coming time to time. Majority of the portion is going to be taught obviously by your batch teachers, but you wanted all of us in this batch, so that's why we are here, along with test series, their discussion, short notes, PDF, recordings of the classes, as well as live classes, interactive classes, strategy sessions, as well as doubt solving and tattva material, solved examples, PYQs, everything material being provided. All of this is in the NEET crash course, and the link is there in the description box. It's just there for 999 rupees. So as you are watching this particular video, just go down in the description box. Okay, just go down in the description box and you can see right over here, there is a link. Join the NEET crash over here. Click on that. You will see it will open up. Okay, it will open up all the things what I have mentioned is right over here. Click on buy full course, enter your details, and your job is done. Okay, so that is something which I feel you should use along with our YouTube classes, because if this course was 5,000, 4,000, even 2,000 rupees, I would be like, yeah, it's okay. Either attend YouTube or this, and you know, I would prefer, okay, just join this thing and fine, you can skip one of the things. But now it's affordable use the resources, use the test series, use the material for extra practice. That's all I would say. Okay, so you can go do both the things hand in hand, right? So that is the advantage of the NEET Crash 2024, which is really affordable. We call it the Crash Course.e, which is excellence, economical, and obviously you have the best of the best things out here, right? Correct. Okay. Thank you so much, guys. Thank you so much for the amazing session and the amazing interaction you guys had. Bye bye, Pratibha, Rajendra, Paul, Sanju, Yashaswini, Swatantra, Jen Lisa, sorry, and Crazy Creations, Komlat, Sanju. Thank you so much, guys. And do not forget to leave a comment below after the session is over on how you have enjoyed. And yes, you can write block 1 physics completed. Block 1 physics completed should be the comment. Bye bye. Take care. Captain Shreyas signing off. Hasta la vista.